Okay, Unit 6. First thing we are going to talk about is we're going to talk about approximating areas with Riemann sums. This is a really big deal. There are 4 types of sums that you need to know. One of them is not strictly a Riemann sum, but we're throwing it in. You've got left sums, right sums, midpoint sums, and trapezoidal sums. So trapezoidal sums are not really Riemann sums, at least to my understanding of it, but it doesn't matter. Sums are the thing that we're doing here. So what I'm going to do is I'm actually just going to show you some animations of doing these so you can kind of follow along. Primarily, these will come from table problems. So here, what we have is we want to approximate the integral from 1 to 10 of f of x dx with a left Riemann sum using the table below. So what you want to do is first write down the integral that you're approximating. Then you want to put an approximately equal to sign. Now, because you're doing a left sum, what you're going to do is you're going to find a delta x and then use the left endpoint, and then the next delta x, the next endpoint. You cannot count on your delta x's being the same. In fact, most of the time they probably won't be the same. So we just step through it. So our first delta x is 2. The left endpoint is at x equals 1. So I've highlighted the box. That's the y value that we're going to use. And then our next delta x is 3. I've highlighted the box. We're going to use f of 3. And then delta x is 2, we'll use f of 6, and then another 2, and we'll use f of 8. And then what you want to do is fill in those values. Now on the AP exam, you do not need to evaluate this. You just leave it. You do not simplify it. Classically, I made a mistake one time while explaining this rule, but we do not want to evaluate this. But on the other hand, I'm just going to do it. So I got 41. So that is a left sum. The next thing we want to look at is a right sum. So in a right sum, you do basically the same thing. You write your integral, you write your approximately equal to sign, and then it's going to be delta x is 2, and then f of 3. And then delta x is 3, f of 6, delta x is 2, f of 8, delta x is 2, f of 10. You write that down, then you fill in the values, and then you stop. But again, I'm going to evaluate it because why not? The next sum that I'm going to do is actually a trapezoidal sum. So I modified the table because trapezoids is a lot of calculations. So for trapezoids, again, write the integral, write your approximately equal to sign. Now, every trapezoid is 1/2 the height, which will be your delta x, times the sum of the bases. So our first delta x is 2. And then what we want to do is the sum of f of 1 and f of 3. So I've highlighted the boxes. Then we're going to have our next delta x is 3, and then the sum. And then our next delta x is 2, and then the sum of these values. So I usually write it out like this. Then what I do is I go through and I fill in the values. On the AP exam, we're allowed to stop there, but for the purposes of the video, I'm just going to do it. That was a different table, by the way. So we got a very different answer. And then the final one that I'm going to demonstrate, because it's the final one that we do, is a midpoint sum. So a midpoint sum requires a very specific table where you can actually find the midpoint. So you write down your integral, you write down approximately equal, and then you need to go, in this case, we're going to go from 0 to 2, which is delta x of 2. But we take the midpoint of 0 and 2, which is 1, find the y value there. So we're doing 2 times f of 1, and then we'll repeat it. So we go from 2 to 6, our delta x is 4. We're going to find the height at the average of 2 and 6, which is 4. So we're finding our height at f of 4. And then we'll go from 6 to 10, our delta x is 4. The midpoint is 8, the height at the midpoint is 2. Then you fill in your values, and you could stop, but again, I'm just going to evaluate it. So those are the sums that we need to do. Let me tell you, table problems are incredibly common. They're going to be on the FRQ almost certainly, and when they are, you're going to have to approximate things. You might also see this on the multiple choice. I mean, every once in a while, it does show up. Another thing that we need to deal with is we need to deal with what kind of error you're getting for each of the various sums. And again, I think that this is first best illustrated. My advice is always draw a picture. If you draw a picture, you're almost certainly going to just get this right. So let's take a look at this. So this one, there's a lot going on at once. I have drawn 2 increasing functions and 2 decreasing functions. And the first thing that I'm going to do is I'm going to draw left rectangles and right rectangles up above on the increasing function. So you can see here we are increasing, and when you are increasing, your left sum is going to be an underestimate, and your right sum is going to be an overestimate. On the other hand, if our curve is decreasing, you can see that your left sum is always an overestimate, and your right sum is always an underestimate. Concavity doesn't actually make a difference on this, even though I made the very poor choice of doing the same concavity and then the same concavity. But concavity doesn't make a difference. I mean, do it on your own. Just sketch on a piece of paper and see what you get. So if you are increasing, then a left sum will underestimate. If you are decreasing, then a left sum will overestimate. If you are increasing, a right sum will overestimate. And if you are decreasing, a right sum will underestimate. And I think I said all of those correctly. Let's take a look at what happens for the trapezoids and the midpoints. And let me tell you, I basically just remember what happens with trapezoids. And you can see here, if you are concave up, you're going to get an overestimate because your trapezoid is just above. And if you are concave down, your trapezoid is just going to give you a underestimate. So trapezoid, just draw the picture. Again, like always draw pictures. But concave up, you're getting an overestimate. Concave down, you're getting an underestimate. On the other hand, the way that I remember midpoints is they do exactly the opposite thing. So you can see here, I'm going to draw the rectangles, and then what I'm going to do is just pivot them into trapezoids that have exactly the same area. But you can see then the tangent kind of like flips, and you're just either over or under. But again, just remember, midpoints do the opposite of trapezoids. So if trapezoids overestimate, then midpoints will underestimate the same curve, etc. But this is what we've got. Right, so I don't know, fun little animation. What I'm going to do now is go back, and I just typed it on the slide as well. So when you're looking for increasing and decreasing, another way of saying that is monotonicity. So a left sum will underestimate an increasing function. It will overestimate a decreasing function. I don't think I need to read all these, but I'm gonna. A right sum overestimates increasing, underestimates decreasing. For concavity, trapezoidal sum will overestimate if you're concave up and underestimate if you're concave down, and the midpoints do the exact opposite of trapezoids. I would say always draw something. That's going to just prevent you from ever getting this wrong. And for midpoints, the only way that I remember them is that they're just doing the opposite of trapezoids. The next thing we want to talk about is limits of Riemann sums. So this is something you might run into in a multiple choice question. I really doubt you would see this in an FRQ. Here's everything in a box. We got the limit as n approaches infinity of the sum from k equals 1 to n, f of x sub k delta x. It's a lot. That's going to be the integral from a to b of f of x dx. In this scenario, x sub k is a, the place where the integral starts, plus k times delta x, and then delta x is just b minus a divided by n. So b minus a is the distance between a and b, the bounds of your integral, and you're dividing them evenly into n slices. So once you really know that, the way that you will run into this is you might be given a problem that looks like this. We want to determine b, which is the upper bound of the integral, for the limit as n approaches infinity, k goes from 1 to n. That's the classic setup. The quantity 1 plus k over n cubed times 1 over n. And that integral we're told is equal to, or that summation, the limit of the summation, is the integral from 1 to b of x cubed dx. So what I look at is, I look at it and I see I can just find x sub k. X sub k is 1 plus k over n. And also, delta x is that thing that's just kind of sitting outside, so delta x is 1 over n. So one approach to solving this is, we already know that x sub k is a plus some stuff, so a must be 1. We also know from delta x that it's b minus a over n, and that equals 1 over n, which kind of implies, or definitely implies, that b minus a is just 1. So if a is 1, and b minus a is 1, that must mean that b is equal to 2. So we have found the value of b. In the next one, I think it's the next one, I'm going to show you a slightly different way of evaluating that, or that concept. So this is one approach though. You can figure out a and you can figure out b minus a and use that. Okay, this is not the one I'm thinking of. It's probably the next one. But another example, a right Riemann sum for f on the interval from a to b. It doesn't actually matter if they said a left Riemann sum or a midpoint Riemann sum. It wouldn't change what you do in this problem. Is given by the sum k equals 1 to n is s of n, where s of n is this weird rational function. N plus 1, quantity 2n plus 3, quantity 4n plus 1 over n squared, quantity 2n plus 1. What we want to do is find the integral from a to b of f of x dx. Okay, so if the summation is equal to s of n, and we know the definite integral is just the limit of the summation, that means the definite integral's value is the limit of s of n. And you can see that s of n, if you expanded the numerator, would give you like 8n cubed plus a bunch of lower degree things. And then the denominator gives you 2n cubed plus n squared, which is a lower degree thing. So really we're just going to get the ratio of 8 over 2. So we just get 4. This turned into a horizontal asymptote or a limit at infinity problem, but our answer here is 4. I'm just telling you, what else are you going to do on this problem, right? Like you're going to plug in a value? I don't know. So like it just kind of feels like it would have to be a limit problem, and it actually is. All right, this is the other one I was thinking about how to figure out A and B. So this is the alternative way that they might present to you a Riemann sum, a limit of a Riemann sum. In my experience, they're always right Riemann sums. I think there's like one example. I don't even think it's an example from a real exam where it was a left Riemann sum, but it could be a left Riemann sum. But anyway, let's look at this. So we have the limit as n approaches infinity of 3 over n, the quantity, and then what we've done is instead of writing a summation, we've actually like plugged in. So we have the natural log of 2 plus 1 times 3 over n, plus the natural log of 2 plus 2 times 3 over n, plus dot, dot, dot. And then we have the natural log of 2 plus n times 3 over n. So you kind of get a feel for it that like delta x is sitting there. You see a lot of 3 over n's. I think delta x is definitely 3 over n. I also think because it's a thing we're plugging into a function, that the function is the natural log of x, and that I'm plugging in 2 plus k times 3 over n, where k is first 1, and then 2, and then visually n in this case. If that's the case, then what I can do is x sub k is a function of k. X sub 0 is always the value of a. So a in this case, just plug in 0 for k and you get 2. X sub n is always the value of b. If you plug in n, you get 2 plus n times 3 over n, 2 plus 3, which is 5. And then the function we're plugging into is the natural log of x. So I think that this is just a right Riemann sum for the integral from 2 to 5 of the natural log of x. If you well, not accidentally, if you look at this and you think the function is the natural log of 2 plus x, then you're going to get different bounds. You're going to get the bounds are 0 and 3, but you can do a u substitution and turn it into the integral from 2 to 5 of natural log of x. Actually be on the lookout for that because it'll be multiple choice. I think that this is the answer that would show up, but you might need to do a u substitution. I should have made that a tip, but I didn't. Maybe I will make it a tip. Who knows? Okay, next topic is a big topic, accumulation functions. So if you watch the first part of this video, I guess, you've already run into accumulation functions because I just had to talk about them. But accumulation functions, basically, if you know a point that a function passes through and you know the derivative of the function, you can rewrite the function as f of x equals f of a plus the integral from a to x of f prime of t dt. That's what we're going to use, right? So it's where you start plus the displacement, basically. When you're doing this, a lot of the values are going to be found geometrically from areas, or it might just be a calculator question. And sometimes when it's a calculator question, you can't really find the antiderivative, so you have to do the definite integral. Keep that in mind. Another thing to look out for is if you evaluate at a value that is less than a, you're going to have to flip the bounds and change the sign. So that means you're just going to, if, for example, if f of x is 3 plus the integral from 2 to x of f prime of t dt, and you need to find f of -1, since -1 is less than 2, you're going to flip the bounds and change the sign and end up with 3 minus the integral from -1 to 2 of f prime of t dt. That's a thing that's going to happen. Now what I want to do is demonstrate visually, I guess, in a little animation style, how we can find some values, right? Okay, so the function that we're working with here is just going to be the integral from 0 to x of f prime of t dt. So right away we know that f of 0 is 0 because the integral from 0 to 0 of anything is just 0. Let's go through the table. So I'm first going to find f of -4. So I'm going backwards, which means I need to flip the bounds and change the sign. Once I do that, I now just need to find the area as I move from left to right. So I'm going to just sweep from left to right. I get that that area is +8, which means that f of -4 is the negative of +8, or -8, and then we just put that up in the table. Now what I'm going to do is I'm going to find f of -6. And instead of going from 0 again, I already know the value at -4 is -8. So I'm just going to say that f of -6 is f of -4 minus the integral from -6 to -4. Why is it minus? Because -6 is less than -4, right? So I'm actually kind of going backwards. But now that I've flipped the bounds and changed the sign, I can just go forwards. I find this area, and I get -4. So what I'm looking for here is the -8 that I had minus -4. So I get -4 and fill it in. Now we're gonna go forward. It's always a little easier to go forward, or it just feels easier, right? So f of 3 is just the integral from 0 to 3 of f prime of t dt. So we're gonna sweep out this area. We get that the area here is -9, so we just get -9, put it in the table. And then again, instead of going from 0 this time, I'm gonna go from 3 because I already know the value at 3 is -9. So f of 6 is going to be f of 3 plus the integral from 3 to 6 of f prime of t dt. That area is 6, so I get -9 plus 6 is -3. So this is how you can go through and find all of these values. I think it's a really useful skill to try to develop, so take a look at a bunch of them, see if you can work it out. It's a good thing to get good at. Okay, let's talk about another huge idea. So accumulation functions are a really big deal. I mean, they really tie together derivatives and antiderivatives, and I think that's why they come up so much. And also just in life, you sometimes know rates of change. So derivatives of accumulation functions are something that we're going to call the second fundamental theorem of calculus, the second FTC. So the second FTC is really just the chain rule, and it says that the derivative of the integral from a to x of f of t dt is equal to f of x. One of the big things that you have to deal with here is make sure that the upper bound is the variable. If the upper bound is not the variable, flip your bounds, change the sign. Got to get that done. And then another form of this, which is the form that comes up most often in multiple choice, I would honestly say the left-hand form comes up most in free response because I think it just makes it easier for them to grade a million papers. But the second form is the derivative with respect to x of the integral from a to g of x of f of t dt is f of g of x times g prime of x. So you take the upper bound and plug it in, and then you multiply by the derivative of the upper bound. That's how I do it in my head all the time. You're really going to need to know how to do this because it's definitely going to come up probably on a free response question. And then the other thing is, when you're talking about these and you're trying to justify things, make sure that if you're given the graph of f prime, which is what you are mostly given, so this is definitely one of the key concepts to succeeding on FRQs. We got to be able to get from the function to its derivative so we can talk all about the derivative. So make sure that you can do that. Okay, the next thing that we want to do is we want to talk about the behavior of accumulation functions, right? That's the whole point of finding the derivative of an accumulation function. So if capital F of x, I hate this notation, but they use it a lot. If capital F of x is equal to the integral from a to x of g of t dt, then we know by the second fundamental theorem that f prime is equal to g of t with the upper bound plugged in, so that's g of x, times the derivative of the upper bound, which is 1. So f prime is just g of x. What that means is f is increasing when g of x is greater than 0, and f is decreasing when g of x is less than 0, as you would expect. And then f is concave up if g is increasing, and concave down when g is decreasing. So another thing to watch out for is you do need to know how to deal with what if there's an extra term. So something like g of x is equal to x squared plus the integral from 0 to x of f of t dt. So I'm going to show you how we can find critical points in that scenario, and I'm going to do it with another animation because I think it's definitely the easiest way to discuss this. So the function I'm going to deal with here is g of x is 1/4 x squared minus 2x plus the integral from 1 to x of f of t dt. We're going to figure out where the critical points of this thing are. Also, maybe we'll try to classify them. Let's also have a graph of f because that's the thing that we're going to be working with, right? So this is a graph of f of x. It's piecewise linear. Now what we're going to do is we're going to find g prime. So g prime is the derivative of 1/4 x squared is 1/2 x, the derivative of negative 2x is negative 2, and then the second fundamental theorem tells us the derivative of the integral from 1 to x of f of t dt is f of x times 1, or just f of x. So if g prime is equal to 0, this is kind of the key. We just take that derivative that we have and set it equal to 0. So 1/2 x minus 2 plus f of x is 0. From there, this is a little weird, but we're just going to solve for f of x. So f of x is 2x minus 1/2. Now, what do we do with this thing? We need to figure out where f of x, the graph that we have, is equal to 2 minus 1/2 x. So what we'll do is just add the graph of 2 minus 1/2 x to the graph of f. And you can see we've done that. And now because I chose some nice functions, we can just see the critical points, right? Everywhere f of x equals that line is a critical point. The critical points are definitely at 0 and at 6. The next thing we want to do is figure out, how do we know if g of x is increasing? Well, if g of x is increasing, that would mean that g prime is greater than 0, which would mean that f of x is greater than 2 minus 1/2 x. And you can just look at the graph and see that. Similarly, g prime is less than 0 if f of x is less than 2 minus 1/2 x. And so what I've done is I've shaded them in horrifying colors. Purple for where f of x is less than the line, so that's where we are decreasing, and then green for where f of x is greater than the line, and so that's where we are increasing. And then we can classify. At x equals 0, g prime is less than 0 on both sides, so there is no extreme value there. On the other hand, at x equals 6, the derivative changes from negative, where we're purple, where f of x is below the line, to positive, where we're green, where f of x is above the line. So that's definitely a local minimum because f prime has gone from negative to positive. Also, I really do not like if you write negative and positive, or like a little minus sign and a little plus sign. I prefer an abbreviation of negative, neg, and an abbreviation of positive, pos, but that may just be me. Okay, the next thing is going to be properties of definite integrals. So there are a couple of properties, I'm sure that you know them. If you have an integral of a sum or difference, it's just the sum or difference of the integrals. If you have a constant multiple, so if you have the integral of a constant times f of x, that's just the constant times the integral of f of x. And they can add up. So if you have the integral from a to b plus the integral from b to c, that combines into the integral from a to c of f of x dx. And I really want to caution you for the exam and for life, the integral of f times g does not equal the integral of f times the integral of g. That will definitely be like a distractor, like one of the wrong answers on a multiple choice question. Do not fall for it. Here's an example that uses properties of definite integrals. And I call this a number line example because it's how we're going to solve it. We're given that the integral from 1 to 10 of f of x dx is 5. We are given that the integral from 3 to 10 of f of x dx is 4. And we are asked what is the integral from 1 to 3 of f of x dx. And so what I do is I draw a number line that has 1, 3, and 10 on it. And then I just kind of fill in the bars of what I know, right? I know that from 1 to 10 I'm given, so I could find that value. I know from 3 to 10 I'm given, so I could find that value. And then just looking at it, the thing we're looking for is the difference between 1 to 10 and 3 to 10, which will be the integral from 1 to 3. So once I have that, I just kind of do it. And so you can see we get the integral from 1 to 3 is equal to the integral from 1 to 10 minus the integral from 3 to 10, which is 5 minus 4, which is 1. Okay, another question that involves properties of definite integrals. Given that the integral from 1 to 6 of f prime of x dx is 25, we want to evaluate the integral from 1 to 6 of 4 f prime minus 6 dx. Believe it or not, this type of thing is on the exam sometimes. So first thing you want to do is break it up into two separate integrals, and also there's a constant multiple rule. So we get 4 times the integral from 1 to 6 f prime minus the integral from 1 to 6 of 6 dx. And then we can just do that, right? We were given the integral from 1 to 6 of f prime is 25. So we have 4 times 25, and then minus 6, you just integrate dx to get x, and then you plug in, you get 6 minus 1. So we have 4 times 25 minus 6 times 5, 100 minus 30 is 70. So we haven't had to really officially use it yet because it was just given. The fundamental theorem of calculus. So we actually did the fundamental theorem part 2 first. Fundamental theorem of calculus says the integral from a to b of f prime of x dx is f of b minus f of a. So we need to be able to find antiderivatives to do this, or just use a calculator, which will also be able to get the answer for us. So you will often have to rewrite this. It's an equation, so you can solve it for f of b. F of b is f of a plus the integral from a to b of f prime of x dx. So that I'm going to call going forward. You're like going forward in time. You're where you started plus your displacement. You can also go backwards in time. You can figure out where you started. So it's where you ended up minus the displacement from a to b. So it's f of b minus the integral from a to b of f prime of x dx is f of a. I use both of those. It's actually my favorite way to use the fundamental theorem is to rewrite it that way. So for accumulation functions, this is almost always, and we already saw it, it's going to amount to looking at signed areas where you are positive or negative based on if you're above or below the axis. You're also probably going to see this when you deal with position and velocity type questions. And then for a lot of problems, this is just going to be calculator. Now, my advice on the calculator section is just use the definite integral. In my class, we use a CAS calculator, which can find antiderivatives. The problem with that is they usually give you something that doesn't have a simple antiderivative. So you have to do the definite integral to get the answer that you're looking for. All right, well, how are you going to find the antiderivatives? You're going to memorize everything that's on this slide, and you probably already have them memorized. Things of note, the integral of a to the x is particularly not sticky in people's brains. All of the antiderivatives that lead to cofunctions get a negative in front of them. And make sure you know the antiderivative of 1 over 1 plus x squared is arctan, and 1 over the square root of 1 minus x squared is arcsine. So of particular note on this slide is everything. All right, let's talk about U substitution. It's one of the big deals. So for U substitutions, advice number 1, do not forget to change the bounds. Advice number 2, do not forget to substitute for dx. Those are the two things that people get wrong all the time. If you're integrating an exponential function, you should let u be the exponential function. Other than that, we're just going to go for it. So again, make sure every x becomes a u if you're doing u substitution on a definite integral. So you need a u, a du, and you need to have u bounds at the end when you look at your integral. I'll show you a couple of examples. I'm not going to belabor this because I'm pretty sure you're all set on this, or I just have a lot of videos on this. So example 1, we're going from 0 to 1, 2x plus 1 to the 5th dx. U is definitely the thing in parentheses, so 2x plus 1, which gives us ultimately dx is 1/2 du. If x is 0, we plug it in, we get 2 times 0 plus 1 is 1. If x is 1, we get 2 times 1 is 2 plus 1 is 3. Really struggling. Our u bounds become 1 to 3, and so we substitute for dx, which gives us 1/2 du. We substitute for the bounds, which gives us the integral from 1 to 3, and we substitute obviously for 2x plus 1, we get u to the 5th. So that's how you do it. For example 2, again, you make your choices based on the easiest, most convenient thing. I think u here is the thing inside the radical. That's a common choice. So x squared plus 4, which gives us that x dx is 1/2 du. We have to change our bounds. So 0 to 2 becomes 4 to 8 because we are plugging in, squaring, and adding 4. That's how we got those. So our original integral becomes 1/2 the integral from 4 to 8 of 1/2 of u to the 1/2 du. Okay, I want to do this third example because it's an integral of an exponential, and I like the advice. One of my students actually kind of taught me this because I was taught to do this a different way. If there's an exponential, just let u be the exponential. If I let u equal e to the 6x to the 4th, then du is 24x cubed e to the 6x to the 4th dx, or the entire original integrand, x cubed e to the 6x to the 4th dx, is just 1 over 24 du, which means my original integral, when I sub, just becomes 1/24th the integral of du, which is 1 over 24 times u plus c, or 1 over 24 e to the 6x to the 4th. I'm finding it very hard to say that. And then plus c. So if there's an exponential, try just letting u be the exponential. It's almost always the right move. I do think that you should be able to do some u substitution in your head. It's not required that you ever do it in your head. But all of these I think are good targets for that because we have a lot of stuff memorized. The basic trig functions I think you should be able to do. I think you should be able to do like a binomial raised to a power. But again, if you can't do it, just show the work. There's just nothing wrong with that. I mean, like row 2 in the middle there, the integral of 4 minus 3x to the 2nd, you're probably safer doing a u substitution. But I think you can do it in your head if you are so inclined. Just wanted to include that. All right, here's another classic example of a u substitution type problem. So we are given the integral from 2 to 10 of f of x dx is 12, and we want to find the integral from 1 to 5 of f of 2x dx. They're just trying to get you to forget to sub for dx here, I think, because otherwise everyone's probably going to just dive in. So if u is equal to 2x, then 1/2 du is equal to dx. We're going to sub for that. The bounds, x equals 1 becomes 2 because we're doubling it, and x equals 5 becomes 10. So when we go to substitute, we have dx is 1/2 du, our bounds become 2 and 10, and then we have f of u du. We know that the integral from 2 to 10 of f of u du, or f of x dx, that's a spelling choice, it doesn't matter, is 12. And so we just get 1/2 times 12, which is 6. All right, there are two big time algebraic techniques that you need to know if you're gonna do this. And the first one is integrating with long division. So basically this will be triggered in your mind if you have a rational function, which is a polynomial over a polynomial, and the degree of the numerator is equal to or greater than the denominator. So the degree of the numerator must be less than the denominator. If that is not the case, step 1 is going to be divide and then integrate. And when you do this process, you get a lot of natural logs in your final answer. So if it's multiple choice, you should look at the answer choices and see if only one of them has a natural log, and if you can't figure out how to do the division, just choose that, but also know how to do it. Sometimes you get arctans, that's if you have like a 1 plus x squared in the denominator. So everybody needs to know how to do this. My first example, you don't really need to do long division. I'm gonna just do the integral of x plus 1 over x. So x plus 1 over x is, just break it up into two things. So x over x plus 1 over x, which is 1 plus 1 over x. So our original integral becomes the integral of 1 plus 1 over x. When you integrate 1, you get x. When you integrate 1 over x, you get natural log absolute value of x plus c. So rewrite it and then just integrate term by term. And just be aware, you're probably going to get a natural log in this process. You might get an arctan. Example number 2, I tried to show the division, but we're doing the integral of x squared plus 3x over x plus 1. So I set up the division. You can look at that if you don't remember how to do division, but this becomes the integral of x plus 2 minus 2 over x plus 1. And then you kind of break it up. You just integrate x plus 2, which gives you 1/2 x squared plus 2x. Then you integrate negative 2 over x plus 1, or you can factor out the negative 2. The integral of 1 over x plus 1 is natural log absolute value of x plus 1. And then we have a plus c. So more of the same. Here's another one. I don't know, the division is slightly harder. Screenshot that if you really want to look at it. We're moving on. All right, the other algebraic technique that you absolutely must know, this applies to A, B, and B, C, is completing the square. So sometimes you have to complete the square and then integrate. In that case, you're almost, I'm going to go as far as to say, well, you're going to get an inverse trig function. You're going to either get arctan or you're going to get arcsine. If there's no radical, you're going to get arctan. If there's a radical, you're going to get arcsine in this process. I think that I'm not lying when I say that. I think that will always happen. Anyway, if you have a quadratic in the denominator that does not factor, probably completing the square. If you have a quadratic in the denominator and you let it equal u, and then when you find du, you're just missing x's in the numerator, it's probably completing the square. So here are two examples. Again, I'm not doing the algebra on this, but the integral of 1 over x squared plus 4x plus 5 becomes the integral of 1 over the quantity x plus 2 squared plus 1, which in my mind I think of as 1 over 1 plus the quantity x squared plus 2. That just gives us arctan of x plus 2 plus c, so that's one example. The next one, a little more annoying because arcsine, it's just more annoying to get these problems to work. We have 1 over the square root of negative x squared minus 6x minus 5. It's a slightly harder completing the square problem, but look up completing the square, get really good at it. I've completed the square. I'm going to let u equal x plus 3, and that'll turn my integral into the integral of 1 over the square root of 4 minus u squared, but there's still a problem because it's not 1 minus u squared. So then I'm going to factor the square root of 4 out, and the square root of 4 is 1/2. So I have a 1/2 1 over the square root of 1 minus the quantity u over 2 squared. That's going to give us an arcsine. Try it, do the substitution there. You should get a 1/2 in the numerator, a 2 on the outside. 2 and 1/2 is 1, which just gives you arcsine of u over 2. And then we sub back in. So completing the square and division are things that everyone needs to know. I'm pretty sure that AB is done with this unit now, so you could jump ahead to unit 7. If you're in BC, you have a couple more things that you need to master. Okay, so BC topic number 1, this is BC exclusive, is integration by parts. You must memorize the integral of u dv is uv minus the integral of v du. There's like a thing you can memorize for this, but I've never memorized it. What I do is I always try to pick dv so that I can integrate it. That's the most important part. You could take the derivative of anything, but you need to be able to integrate dv. And then there's just a couple types of problems that you're going to run into when you're doing these. The first one I would say is just like standard integration by parts, right? So if we have the integral of x e to the 2x, polynomials are a great choice for you because eventually the derivatives go away. And also, I can integrate either x or e to the 2x, so I'm definitely going to choose u is equal to x, because the derivatives eventually go away. That is kind of a mental rule that I use. So I get my du, I get my v, and then it's uv minus the integral of v du, and then I just integrate 1/2 e to the 2x, and I get x over 2 e to the 2x minus 1/4 e to the 2x plus c. For example number 2, I chose it specifically because a lot of negative signs show up. So it's the integral of x sine of x. I'm going to make u equal x, I'm going to make dv equal sine of x. Honestly, if you choose wrong for your u and your dv, it's like usually your integral that you end up with just is harder than the original. That means like back up and switch your choices. But if I make these choices, then du is dx, v is negative cosine of x, And so we get uv x, negative x cosine of x, minus the integral of v du. So it's minus the integral of negative cosine, which is basically plus the integral of cosine, which is just sine. So we get our answer there. So watch out for the double negatives. They're a killer on these. Okay, another type of problem that I particularly like is where you're given essentially an integration by parts problem, but you're just given weird information. So for example, here we are told to evaluate the integral from 2 to 4 of x squared f double prime of x dx. And we have a table of values for f, f prime, and f double prime. Also, we know that the integral from 2 to 4 of f of x dx is 6. So there's just a lot of setup for this. So I've done the work here. First up, we're doing integration by parts, right? So it's 2 to 4 of x squared f double prime of x dx. I make my choices. I've got u is x squared, dv is f double prime. Mostly because what are you going to do? If you end up with f triple prime, you don't know anything about it, so that can't be u. So u is x squared, dv is f double prime, which makes du 2x dx and v f prime of x. So we set it up. We have uv minus the integral of v du. So v du is 2x times f prime of x dx. You look at that and you're like, oh no. This is another integration by parts. Also, because there are bounds, I like carried them through, but I actually think a better idea is to do an indefinite integral and then just evaluate from there. I actually think that's a better choice, but I didn't do it. So, and once you've typed all of this, you're not going back, right? So we have another integration by parts. So I'm gonna carry the integration by parts down here and just do this one and then kind of combine everything at the end, which is dangerous. So for this one, we make our choices. U is 2x, dv is f prime of x, du is 2 dx, v is f of x. So we do it. We have uv, which is 2x f of x, and that's going from 2 to 4, minus the integral of v du. So v du is f of x times 2 dx, and you can factor out the 2, so you get 2 integral from 2 to 4 of f of x dx. We were given the integral from 2 to 4 of f of x dx. That's 6. So that's negative 2 times 6. So at this stage, we now have 2x f of x from 2 to 4, and then minus 12. Now what we want to do is combine those. I didn't do the best work on this. From that first line up there, we have x squared f prime of x from 2 to 4, minus the thing we just got. So it's minus, and then our 2x f of x from 2 to 4, minus negative 12, so plus 12. I don't know, this is not the best work that I've done in this video. I think we can all admit that. And then I just subbed in, I don't know, screenshot this and try it on your own. It's a good problem. I think the final answer is 52. Okay, the next algebraic technique, I guess, that you need to know if you're in Calc BC, but not Calc AB, you should already be on the next unit if you're in Calc AB, is partial fractions. So partial fractions, the only thing you need to know are non-repeating linear factors. For non-repeating linear factors, they always basically look like a over, let's say like m times x minus a plus b over, I don't know, m2 times x minus b. Here I've just written x minus a and x minus b, but there might be a coefficient. So always non-repeating linear factors. When you do this process, you will always get natural logs when you find your antiderivatives. And honestly, these will probably be involved in improper integrals because there's kind of like a neat thing that shows up that you just have to know how to do. So let's take a look at the main technique that you are going to use to find a and b, which is called the cover-up method. So for the cover-up method, what you're going to do when you want to find a, first of all, you have to have factored everything. You're going to set it up. So it's a over the first factor plus b over the second factor equals the original numerator over the factored denominator. Now, to find a, the thing that makes x minus 2 0 is 2. So what we'll do is we will cover up the b part. It's not relevant right now. Cover up the x minus 2. A is just going to be 5x plus 1 over x plus 3. When x is 2, you plug in, you get 11/5. To find b, you cover up the a part, and you also cover up the x plus 3. The thing that makes x plus 3 equals 0 is negative 3. So we're going to plug in negative 3. We get 14 over 5. So the decomposition is 11 over 5 quantity x minus 2 plus 14 over 5 quantity x plus 3. And that's how you do that. And then you just want to integrate that, but that's just natural logs, right? 11/5 natural log absolute value of x minus 2 plus 14 over 5 natural log absolute value of x plus 3. Here's another example. To find a, we plug negative 1 in on the right-hand side while we've covered up x plus 1. Gives us 11 over 5. To find b, we plug 4 into the right-hand side while covering up the x minus 4. That gives us 24 over 5, which decomposes. And then you can see if you integrate that, you're getting natural logs. Like The hard part here is the algebra. It's not usually the antiderivative. Okay, the next topic that you need to know if you're in BC but not AB is improper integral. So improper integrals I think of as integrals that make the fundamental theorem unhappy. So the fundamental theorem wants you to have constant bounds, and it wants you to have an integrand that is continuous on the closed interval containing the bounds. Improper integrals break those rules. So the first type is you have an infinite bound. So you could be going from 1 to infinity of 1 over x cubed, for example. You could also have a discontinuity. So you could be going from 1 to 2 of 1 over the quantity x minus 2 to the 2/3. The problem there is that if you plug in 2, you get 0 in the denominator, and that's bad. It is possible that you will get a finite value when you do these. It's also possible that they still diverge. Don't lose track of that. It's entirely possible that you get a divergent thing when you do this. I would say one of the most important parts about improper integrals is you are going to lose a point if you do not use the proper notation. So the proper notation is you cannot have infinity as an upper or lower bound. So if you have 1 to infinity, 1 over x cubed, you're going to change that to the limit as b approaches infinity of the integral from 1 to b of 1 over x cubed dx. It's really picky. It's just a thing that you have to do. And then, for example, if you had the integral from 1 to 2 of 1 over the quantity x minus 2 to the 2/3, because the problem is happening at 2, we need to approach 2. Since you're from 1 to 2, the only way you can approach 2 is from the left. So we change our integral to the limit as a approaches 2 from the left, the integral from 1 to a of the integrand. So it's really picky, but that's what you got to do. You have to use the limit or you're definitely going to lose a point. And you don't want to lose points. All right, here's an example of a divergent one, which I think is really important because this is the one that screws people up the most, and it's recently been on FRQs. So, well, not this, but this concept. Evaluate the integral from 0 to 3, 1 over the quantity x minus 1 dx. Step 1, you notice that there's a problem at 1. This is the main thing that people miss, right? Like people, if you just integrate this, natural log absolute value of x minus 1, and then you try to plug in 3, you plug in 0, you walk away, you've gotten it wrong. The problem is 1 over x minus 1 is not continuous on 0 to 3, so we have to break it up at 1. So integral from 0 to 3, 1 over x minus 1 dx becomes the limit as b approaches 1 from the left, 0 to b, plus the limit as a approaches 1 from the right of a to 3. So we've broken it up into 2 integrals. Once you've done that, and this is the key thing, just evaluate one of the integrals. If you get a finite number, move on and do the second integral. If you do not get a finite number, you are done. The answer is diverges, and you never even do the other integral. So in this case, if I work on the first one, the limit as b approaches 1 from the left, I just integrate. So I have the limit as b approaches 1 from the left of natural log absolute value of b minus 1 of x minus 1 from 0 to b. Plug in b, limit as b approaches 1 from the left, absolute value of b minus 1 minus the natural log of 1. Natural log of 1 is 0, we all know. And then if b approaches 1, I get, I'm putting air quotes around this, not that you can see me, we get the natural log of 0. But as you approach 0, natural log approaches negative infinity, right? It's always a good idea to graph natural log just to see that. So we get negative infinity. That is not a finite number. This integral diverges. Do not do the other part. Just don't waste your time. If either integral diverges, you are done. Whole thing diverges. And then sometimes you're going to have to use partial fractions and an improper integral. And so you're going to get some natural logs. So I'm not going to talk all the way through this. We have the limit as b approaches infinity, the integral from 1 to b. So I've already set it up so that I can get the points. 7 over 3x minus 2, 2x plus 1. I did the partial fractions. I got 3 over 3x minus 2 minus 2 over 2x plus 1. I rewrote it as a broken up integral. Then you can do each part of the integral and you just get natural log of 3x minus 2 minus natural log of 2x plus 1. Now the problem is, if you try to have b go to infinity for that, you get infinity minus infinity, which is kind of an indeterminate form. So the thing you want to do is use properties of logs. You have a log minus a log. That becomes the log of the first thing over the second thing. And now you use your limit, right? If I take the limit of this, I just end up with the limit of natural log of 3b minus 2 over 2b plus 1. But that definitely just goes to 3 halves as b goes to infinity. So I really have the natural log of 3 halves minus the natural log of 1/3. By properties of natural logs, that's the natural log of 3 halves divided by 1/3, or the natural log of 9 halves. But the real takeaway here is when you have the limit as x approaches infinity of the natural log of f of x minus the natural log of g of x, the first thing to do is rewrite it of the limit as x approaches infinity of the natural log of f of x over g of x. All right, unit 6 is a beast. I think we're done. We're moving on to Unit 7. Okay, Unit 7 is all about differential equations, so we need to know what a differential equation is. Differential equation is really any equation that includes a derivative, so you see them all the time. We got dy dx is x squared minus 3x. That is actually a differential equation. db dt, implying that time is involved somehow. 0.08b, so notice that is the dependent variable in there. Or we could have like dv dr is 4 pi r squared, all kinds of things. One thing that I think it's important to know is you're gonna have to be able to like read a description of a differential equation and figure out what the equation is. I just wanna point out two of them that are, I don't know, pretty obvious and they come up a lot. The first one is if y equals f of x, so if the solution curve is increasing linearly, that just means that you have a linear equation. And if you're increasing linearly, that means that dy dx is equal to k, or the slope of the line. So when you see increasing linearly, the differential equation that you would choose in multiple choice would just be dy dx equals k. People find that one really confusing. The next one, not as confusing, but if weight is growing at a rate proportional to the current weight, and you could replace weight with basically any word there. So if weight is growing at a rate proportional to current weight, we would say that dw dt is k times w. As far as the AP exam is concerned, inversely proportional does not exist. It will always be directly proportional, so it's always k times whatever they then describe. So don't be afraid to put the independent variable in your differential equations. When you're given a differential equation, you're often going to have to describe what the solution curves look like, even if you don't solve the differential equation. So that's an important point. So what we're doing is describing the solution. So if a solution is increasing or decreasing, that's going to come from the sign of dy dx. So if dy dx is greater than 0, f is increasing. If dy dx is less than 0, f is decreasing. This is the same as what you did when you would like find a derivative and make a sign chart. But now you're dealing with differential equations. Concavity is still the second derivative. So if you're trying to describe where the solution curves are concave up, you just set the second derivative greater than 0 and see what relationship you get. And concave down, you set the second derivative less than 0 and see what relationship you get. Relative maximums and minimums are mostly going to use the second derivative test if dy dx has a y in it. And the reason for that is that it's just really hard to make a sign chart if you have x's and y's. Like, how are you testing to the left or the right of something? Like, what is to the left or the right if you're basically in a plane type situation instead of a number line or a sign chart? So second derivative test is really big with differential equations. The other thing is, as I kind of alluded to there, you're gonna end up with relationships. Like you might end up with 2x plus 3y is greater than 0 when you're trying to find where the relationship between x and y when the solution curves are increasing, for example, or concave up. So don't be afraid of that. We're gonna do a couple of examples to see how to like describe these scenarios. Okay, example usage number 1. Given dy dx is 3x minus 5y plus 2, we want to find the relationship between x and y such that the solutions are increasing. So you might see this on multiple choice, you might see this on FRQs. For my solution, increasing means dy dx is greater than 0, which means 3x minus 5y plus 2 is greater than 0, which means negative 5y is greater than negative 3x minus 2. I'm basically just trying to isolate y so I can describe things. I'm going to divide by negative 5, flip the sign, so I get 3x plus 2 over 5, or y is less than, I should say, 3x plus 2 over 5. So now I need to describe that. So I would describe that as the solutions are increasing in the half plane, because you're cutting the plane in half with this line, the half plane that is below y equals 3x plus 2 over 5. And if we want to know what that looks like, here it is. I've drawn kind of a slope field. It's not really perfect, but it's pretty close. And then I drew the line and I shaded the region that we're talking about. And you can kind of see visually that those solutions are in fact increasing. All right, example number 2. If we're given that dy dx is 4x plus 3y minus 2, we want to describe the region on which all solution curves are concave up. So it's like kind of the same question, except in this case, we're going to have to take a derivative. Since we know dy dx is equal to 4x plus 3y minus 2, any derivative of y is not 1, it's dy dx. So our second derivative is 4 plus 3 dy dx, the derivative of negative 2 is 0. So then we get that equals 4 plus 3 times replace dy dx with 4x plus 3y minus 2. And then simplify it, we get 12x plus 9y minus 2. Now we need to deal with the concavity. Concave up means second derivative is positive, so we just have that relationship is greater than 0. Solve for y, you get y is greater than 2 minus 12x over 9. So my description again would be all solution curves are concave up in the half plane above the line y equals 2 minus 12x over 9. And here's the slope field with the shading again, just in case you're interested. It is a good way to like visualize things, but nobody's making slope fields by hand anymore. Okay, using the second derivative test with a differential equation is a big deal. So let's look at one. Given dy dx is 2x plus 3y minus 4, which may be the thing we were just dealing with solution y equals f of x passing through the quantity, nope, not the quantity, the ordered pair 5, negative 2. Determine if y equals f of x has a relative max, relative min, or neither at the point. So the way that I'm going to handle this is first I'm going to see if dy dx is even 0 at that point, and I'm going to kind of hope that it's not. But when I evaluate it, I get dy dx is in fact 0 at that point. Until recently, the answer was always going to be maximum or minimum, but they seem to have kind of changed their opinion on that. And so now sometimes you actually will get neither, and it feels like such a waste of your time. But you plug in, you'll get like dy dx is 12. And you're like, that's not 0. That can't be a max or min. So then the answer is neither because dy dx is not 0. Once you have dy dx is 0, you need the second derivative. So we basically just do what we did last time, right? We're finding the derivative with respect to x of 2x plus 3y minus 4, which gives us 2 plus 3 dy dx because the derivative of y is dy dx. We already know dy dx is 0 at the point we're interested in, so I'm not going to substitute in again, but if you did, that would be fine. I'm just going to say the second derivative is 2 plus 3 times 0, which is the value of dy dx, which is 2, which is greater than 0. And since we have a horizontal tangent line and we are concave up, that must be a relative minimum. So you're going to be using the second derivative test with differential equations kind of a lot. It's like the main place that I find myself using it. Verifying solutions is a topic that I hate on the AP exam. Not because it's hard, it's not. It's just that it shows up in multiple choice and you basically just have to do the problem like 4 times. You have to take option A and see if you can plug it in. Take option B, plug it in. I don't really think there's a better way to do them, unfortunately. Or maybe someone will comment and explain to me how we're supposed to be doing it, because that's what I tell my students to do every year. So to verify a solution, what you do is you substitute it and its necessary derivatives into the equation and see if you get a true statement. So if we want to verify that y equals sine of x is a solution to the second derivative plus y equals 0, so we are verifying, so it's going to work. But on the AP exam, it would be like, which of the following is a solution? So I need to know what y is, it's sine of x. I need to know the second derivative, which means I need to get the first derivative. So dy dx is cosine. The second derivative is negative sine. And then you literally just plug in. The second derivative is negative sine, so you replace it. The value of y is sine, so you replace it. Negative sine plus sine is 0. Verified, that is a solution. So that's annoying. It definitely shows up on multiple choice. And when it does, I'm always like, I don't know what I'm supposed to be teaching to make this work or to make it work faster. And if you look in the archive of all FRQs ever, they definitely in like the 60s and 70s, maybe in the 80s, would actually put this on FRQs. I'd be very surprised if it shows up now. But maybe it will, I don't know. That's why we're doing this. All right, a cool thing that you can do that has shown up more recently is they will tell you the form of a solution to a differential equation. So for example here, find the constants m and b so that y equals mx plus b satisfies the differential equation dy dx equals 2x plus 3y. So what I'm going to do here is I'm going to take this from the approach of this will work on any given equation that they give you, right? So step 1 is they gave you y equals mx plus b. We're just going to take the derivative of that. The derivative of y equals mx plus b is m. The next thing we know is if we have dy dx is 2x plus 3y and y is equal to mx plus b, we can substitute that in and get dy dx is 2x plus 3 times the quantity mx plus b. And then if we factor that, we get the quantity 2 plus 3m times x, and then there's just a 3b hanging out on the side. So the coefficient of x in both of our expressions for dy dx has to be equal. There's no x in the first one, so its coefficient is 0. On the second one, the coefficient is 2 plus 3m, so 2 plus 3m must equal 0, which automatically tells you m is negative 2/3. The other thing that we know is the constant term, the term that has no x with it, must also be equal, so m from the first one must be equal to 3b, and we just figured out that m is negative 2/3, which means b must be negative 2/9. I would recommend that you just take a look at this like right before the exam, just in case, just to refresh. It's not really a big deal, but if it's on it, it's not hard to get the points, and I want you to get every point possible. All right, sketching slope fields. I've shown a couple slope fields. Sometimes in the past, they would make you sketch them by hand. I do not think that would be on the FRQs anymore, but obviously Everyone's going to comment if that is the case. When you have to sketch your own slope field, you basically just like pick x, y, compute the slope, then you draw a tiny little segment with that slope. It's like you're drawing a little tangent line, and then you repeat over and over again. I think this won't be on the FRQs anymore because the FRQ booklet is completely blank, and they used to give you a field on which to do this and like specify the points. Maybe they'll go crazy and tell you to personally draw and then fill in a slope field. We'll see. Instead, on multiple choice, what you're definitely going to have to do is either match a slope field to a differential equation or a differential equation to a slope field. Doesn't really matter, the process is basically the same. Here we just have a slope field. I've drawn some solution curves. It's actually kind of irrelevant to the problem, but I think it looks nice. So one is you can personally just trace in solution curves. That can very much help you. We're gonna look at that on another thing. I often will just look for where the slope is equal to 0, because if I can figure out the slope is always 0 when x is equal to 2, I look at all the slope fields and I just see which one has 0 slopes everywhere x is 2, for example. You can see if the slopes stay constant on vertical lines. If moving up and down does not change the slope at all, that means your differential equation does not have a y in it. On the other hand, if moving left and right along horizontal lines doesn't change the slope, that means that x is having no impact, which means the differential equation only has y in it. Another thing you can do is check the signs by the quadrant that you're in. So for example, in the first quadrant, x and y are both positive, see what happens. Then in the second, x is negative, y is positive, etc. That's a very powerful technique. And then another thing that works on almost every multiple choice, but I feel like is giving up, but is probably the best strategy, is just pick one point and plug it in and see what slope you get, and then look at all your slope fields. Or look at a point on the slope field, choose it probably on the x-axis or the y-axis, see what the slope is, and then take that and plug it into the answer choices. That can usually knock it out on its own. I just don't love that technique. Okay, let's talk about a method that we can use. So I mentioned we can try to visualize or sketch solution curves on the slope field that we're given. If we do that, we can figure out the function, maybe, potentially. If we can figure out the function, then we'll just take its derivative, because when you sketch a solution curve, you're thinking that you've solved the differential equation, which means the differential equation is the derivative of the thing you got. So on these slope fields, if I were to draw in solution curves, they would look like this. Looks sort of vaguely like sine of x plus c to me. And then the other one looks roughly like cosine of x plus c. So to get the differential equation, I just differentiate those. So if I think it's sine of x plus c, the derivative of that is cosine, so dy dx should be cosine of x. Now what might happen in a multiple choice question is maybe the option is 0.5 cosine or 3 cosine, right? That would be like a y scaling issue. But what I definitely know is that it's not negative 3 cosine, because the derivative of sine is not negative cosine. And then for the other one, if it looks like cosine, the derivative would be negative sine, and we would be picking that. So you're looking at the solutions to the differential equation. You're not looking at the graph of the differential equation. That's something to really keep in mind. Okay, the horizontal solutions are really important when you're trying to match a differential equation or just kind of think about the slope field for a differential equation. The reason that's important is if y equals a constant is a solution, then plugging that value into the differential equation should give you 0, so that's one reason. Another reason it's important is that horizontal lines divide the plane. There's points above it and there's points below it. If I'm looking at this and I see that I think y equals -2 is a horizontal solution, that means that y plus 2 should be a factor. And since there's only one horizontal, I'm thinking it's now k times the quantity y plus 2. If I look at the point 0, 1, at 0, 1, the slope is negative, which means when I plug 0, 1, or when I plug 1 in, I need to get a negative slope, so I think the coefficient is just negative. So I think negative quantity y plus 2 works, but any negative k value would probably work for this, just depends on how steep the segments are. You can see on the other one, it's basically the same idea. There's a horizontal line at 0 and a horizontal line at 2, which means that the factors should be y and y minus 2. So now I just have k times y minus 2. And what I want to do is, I don't know, test a point, right? So if I'm between 0 and 2, I need to get a negative slope, you can see. If I'm above 2, I need to get a positive slope. If I'm below 2, I should get a positive slope. So for example, if I let k equal 1, then when I'm between 0 and 2, I will get a negative, and that works. And so I would choose that, or anything with a positive k value will actually work in this case. Finding particular solutions to differential equations is a huge topic. It basically just means solve the differential equation and solve for C. One of my students once came to me after the AP exam and told me they didn't know what it meant to find a particular solution, and I died a little inside. It just means solve for C, like don't leave C. You're gonna use the point that they give you to solve for C, and College Board just does not care how crazy your C value looks. So like it could be all over the place. Here's an example. We want to find the particular solution to dy dx equals e to the 2x plus sine of pi over 12x that passes through 3, 2. So this one, we can just say that y is definitely the integral of that thing. When I integrate e to the 2x, I get 1/2 e to the 2x. When I integrate sine of pi over 12x, I get negative 12 over pi cosine of pi over 12x. If you need to do a u substitution, just do it. Don't think about it. And then we put a plus c. Forgetting plus c is one of the greatest tragedies in all of calculus. We then know that the point 3, 2 is on this curve. So we plug in 2 for y and we plug in 3 for x. And you can see this is starting to get gross. We get 1/2 e to the 6 minus 12 over pi cosine of pi over 4 plus c. When we simplify that a little bit, we get 2 is equal to 1/2 e to the 6 minus 6 root 2 over pi plus c, which makes c 2 minus 1/2 e to the 6 plus 6 root 2 over pi. That's a crazy value of c, but like I said, they just don't care. They just want you to do it correctly. So then when we solve for y and sub in our c, this is what we get. I'm not going to bother to read it. You can see it. The next thing, and one of the most important techniques, is to separate and integrate. So separate and integrate means move all of one variable to one side, including the dx or the dy. Move all of one variable to the other side, including the dx or the dy. Basically, y ends up on the left and dx ends up on the right 100% of the time, or whatever. The dependent variables on the left, the independent variables on the right. You're going to want to keep the negatives on the side with the independent variable whenever possible. I'm going to show you an example of that. And then another thing that you definitely want to do is you want to put your plus c on the side with the independent variable. So that's an important factor. So I'm not going to solve one on here. I'm just going to show you what I mean by that negative thing. So if dm dt is 12 minus m, my first step would be to rewrite it as dm dt equals negative quantity m minus 12. And then I separate. I get dm over m minus 12 is equal to negative dt. The reason that I'm doing that is that when I then go to integrate, on the left-hand side, I don't have to deal with the chain rule, and I'm not going to forget an extra negative sign. It's definitely the way to go. So to reiterate, do not bring over a negative coefficient. Factor it out, leave it on the side with dt or dx or whatever. Just leave it on the right-hand side. Okay, let's do one where we separate and then we integrate and then we use our initial condition. So we want to solve dy dx equals y times the quantity x plus 5. And we know that y of negative 5 is equal to 10. So we separate. We get 1/2 dy is the quantity x plus 5 dx. We throw some integral signs on that. The antiderivative of 1 over y dy is natural log of the absolute value of y. On the right-hand side, we get 1/2 the quantity x plus 5 squared, or you get 1/2 x squared plus 5x, and then a plus c. It doesn't matter which one you go with, you'll get the same answer. Your c will look a little different, but it doesn't make a difference. So now what we want to do, also notice I put plus c on the side with x. That's what you're going to do all the time. Now what we're going to do is we're going to exponentiate and simultaneously change the original c into a new value of c. I have a lot of videos where I explain this. I do this every time. I highly recommend it. So we get y is equal to a new value of c, e to the 1/2 quantity x plus 5 squared. I should probably have made a bigger deal of this on the slide. If y ends up in a natural log, exponentiate before you solve for c. Your old c will become a new c as a coefficient, and it'll take care of the absolute value by itself. That's kind of the ideal scenario. Now we just need to solve for c, so we take negative 5, 0, and sub it in. We sub in 10 for y. We get equals c e to the 0, because 1/2 negative 5 plus 5 is 0. E to the 0 is 1, which means c is 10. So our answer is y equals 10 e to the 1/2 quantity x plus 5 squared. Okay, the next thing is really important. It's to pay attention to the initial condition. There are two ways it will matter. It will affect the domain potentially and the range potentially of your solution curves. So for example, if we have dy dx is 1 over x plus 3, we know that that x plus 3 is causing a problem, right? There's a problem at x equals negative 3, which means our solution must either have a domain of x is less than -3 or x is greater than -3. It will not be both. Once you've established that, if you're given y of -5 is 10, -5 is less than -3, so the domain is x is less than -3. If you were given y of 4 is equal to 6, you just look at that x, it's 4, that's bigger than -3, which means we need the domain x is greater than -3. If they do not ask you for the domain on your solution, you do not need it. It will not be given a point value. You will not lose points for not putting one. I don't think you'd lose points for being wrong, but why would you ever want to put something that's wrong, right? So if they don't ask for the domain, you don't need it. If they do ask for the domain, this is how you figure it out. The other thing is, the solution to a differential equation is a function that's continuous. That's the issue here, on an interval containing the initial condition. So because we need it to be continuous, that's why we're choosing one of the domains over the other. The other way the initial condition can impact your solution is the range. So the initial condition actually determines the range of the solution, right? If you are solving and you end up at the point y squared, this is really where it comes from, y squared is equal to x plus 4, that means that y is either the positive or negative square root of x plus 4. If your initial condition has a positive y value, like y of 0 is 10, that's bigger than 0, you're going to choose the positive square root. If you start with y of 0 is -5, which is less than 0, you choose the negative square root. That's how you can decide which one to choose. Sometimes on multiple choice questions, just looking at the domain and range is enough to answer the question. Sometimes on multiple choice, it's actually enough to just plug in the initial condition and it'll wipe out one or two of the answer choices, which is just a great technique. And here I'm just reiterating again, the solution is a function. That's why we have to choose either the positive or negative square root. That's continuous, which is why we have to choose the domain on an interval containing the initial condition. So the initial condition is doing a lot of work. If you were in Calc AB, you are done at this point. If you were in BC, we are going to move on and talk about a couple of additional things. The first one is Euler's method. So Euler's method, it's just a lot of tangent, I'm going to say things. They're kind of like tangent line approximations, but you use points that aren't strictly speaking on the function, but it's just using tangent lines over and over again. My recommendation, always use a table for these, and I'm going to show you the table in a second. You are always approximating when you do this, so always use approximately equal to at the end. To find a new y value, you just take the old y value plus the delta y that you calculate. And here's the information in the table and the table itself. So delta y is delta x, which is the number one thing people forget. People just forget to multiply in delta x. Delta x times dy dx at AB, which is just the point in that row of the table. So you're always going to use the table. It does represent the work that you were doing. So you don't have to wonder, like, is this work good enough? Did you do the table? If so, yes, your work is good enough. Okay, let's take a look at an example. Euler's method, 2 steps of equal size to approximate f of 2, given that f of 1 is 4 and dy dx is 2x plus y. Step 1, we need to get from 1 to 2 in 2 equal steps. So that's 2 minus 1 divided by 2. Delta x is 1/2, and we're going to not forget to use it. We set up our table. This first thing you do is you put 1, 4 in the table, right? Because that's the given. Now, delta y is delta x, which is 1/2. And now you plug 1, 4 into the differential equation. So you get 2 times 1 plus 4. That's 6 divided by 2 is 3. To get your new y value, you just do the old one, 4, plus this delta y. So 4 plus 3 is 7. Our delta x is 1/2, so we just always are incrementing x by 1/2. So now we're at 1.57. We're going to take that. We have delta x, 1/2, plug 1.57 in, you get 2 times 1.5 is 3, plus 7 is 10. 10 divided by 2 is 5. So we have our old y value 7, plus delta y is 5, so 7 plus 5 is 12. So we get 212. The important thing now is we have to say that f of 2 is approximately 12, not equal to 12. You don't want to do all this and then lose a point for that. That would be ridiculous. Some exam advice, it's not really advice, it's just crazy. One time they actually had Euler's method, but delta x was 1, and it just felt so weird. I think there was actually a case where they had you use Euler's method with only 1 step, which is weird because that's literally just using a tangent line. Example number 2, Euler's method, 2 steps, equal size. We want to approximate f of 0 this time, given that f of 1 is 4. So it's really the same problem, but I just want to point out, delta x can be negative, right? We are going from 1 to 0, so our delta x is 0 minus 1 divided by 2, or negative 1/2. You have to be going backwards. So the work is all identical. Our delta x is negative 1/2 this time, So we work it through, we end up at 0, 0. So we would say f of 0 is approximately 0. And I just want it in your mind, it's okay for delta x to be negative. That is not a weird scenario. Okay, another thing I just want to point out really quickly is because Euler's method is just using tangent line approximations, concavity will determine if you're getting an over or underestimate, just like it would with a normal tangent line. So if your function is concave up on the entire interval, that means that you're going to get underestimates from Euler's method. If your function is concave down on the entire interval, you're going to get overestimates. It's been a long time since they asked that. I'm not even sure I remember them actually asking it, but it's a valid question. So be on the lookout for that. Don't get confused. Euler's method is just like lots and lots of little tangent segments. At this point, I just want to summarize for us because we know a lot of ways to approximate things. I'm not going to do any problems here, but we could use a tangent line to approximate something. We could use the fundamental theorem and rewrite it and use like a Riemann sum, a left, a right, a midpoint, or a trapezoidal sum to approximate. We could use Euler's method to approximate a value, and ultimately we'll be able to use Taylor's series to approximate. That's a lot of ways of approximating. There was once an FRQ, a BC FRQ, where you actually just had to use 3 of these methods, and that was the entire question. It was kind of a neat question. I really liked it. But it's definitely a thing. Okay, another uniquely BC topic is the logistic differential equation. The only reason that this is a BC exclusive topic is that you need partial fractions to solve this differential equation, and we don't do those in AB. So it's not hard, it's just they're kind of gatekeeping it with that technique. So you can see the slope field here. I have one solution that's decreasing that starts above that horizontal line. I have 2 solutions that are increasing. They start below the horizontal line. That's going to be a big deal. Every time you're dealing with this, you always want dy dx to look like k times y, the quantity 1 minus y over L. If it looks like that, then everything that you have memorized applies. If it doesn't look like that, the things you have memorized do not apply, and so you shouldn't try to apply them. So if it's not in that form, factor it until it is. That's crucial. Once it's in that form, the limit as x approaches infinity of y equals f of x, the solution, is just L. So you can actually just read it off the differential equation. That's probably the single most common question that they ask. Another thing, y equals f of x, the solution, will always have a point of inflection when y equals L over 2. That's actually only true if you start off with an initial condition below L, but that's definitely the most common thing that you get. We can also talk about concavity. So if y is less than L over 2, you are definitely concave up. If y is between L over 2 and L, you are concave down. You can kind of look at the slope field and see that. In terms of increasing and decreasing, if you start out below L, you're always increasing. If you start out above L, you are always decreasing. Another thing that we could talk about that I think is a valid multiple choice question, or I guess an FRQ, would be the range of your solution. So if your initial condition is less than L, the range will be from the initial condition, y of 0, to L. You include the initial condition, obviously it's the initial condition, but you actually never get to L, so that's going to be an open interval on that end. And the opposite is also true. If you start out with an initial condition that's above L, you're just going to decrease until you get to L. So in that case, your range would be from L to y0, where you include y0, but again, you never include L. Just doesn't make it. Okay, we're going to do 2 examples with logistic. The first one, we are given that y equals f of x satisfies y of 0 equals 6, where dy dx is 50y minus 25y squared. We want to find the limit as x approaches infinity of f of x. So our solution looks like this. Step 1, factor the differential equation. dy dx is, you can take 25y out, you get 25y, the quantity 2 minus y. That's still not good enough. We need it to be 1 minus something. So we take a 2 out. When we take a 2 out, we get 50y, the quantity 1 minus y over 2. Once it looks like that, we know that L is 2, which means the limit as x approaches infinity of f of x is just 2. The next question is like the same exact question, but what I have done is I changed the initial condition. Don't get fooled by that, right? If y of 0 is equal to 1, it doesn't change anything. It's kind of weird. dy dx still factors down to 50y quantity 1 minus y over 2. The limit L is still 2, which means the limit as x approaches infinity of f of x is still 2. It doesn't matter what the initial condition is. There's actually an example of an FRQ. I don't remember. It might be like the late 90s or the early 2000s. I know a lot of FRQs. Like I've spent too much time with them. where they just gave you two separate initial conditions and asked for the limit. It was kind of crazy. It was like very free points. Okay, example number 2 here. If dy dx is 20y, quantity 18 minus y. So you see a theme here where you're gonna have to factor this thing. Be on the lookout for the logistic differential equation though. If you can write it, just do it. Find the value of y when f is increasing at its greatest rate. Okay, so the solution here, we're gonna factor again. So I gotta take out an 18. I get 360y, quantity 1 minus y over 18. So we automatically know that L is 18, which means there's a point of inflection at L over 2. So the point of inflection is at y equals 18 over 2 or 9. So the value of y is definitely 9. It's also a good question that they could ask and sometimes do. What's the actual rate of change at that point? So all we have to do is take y equals 9 and plug it back into the differential equation, and we will get dy dx when y is 9 is 20 times 9 times 18 minus 9, which is 81 times 20 or 1620. So that's what we got for unit 7. Let's move on to unit 8. All right, unit 8 is all about applications of integration. So let's take a look at the first thing we're going to talk about, which is average value. So average value is the integral divided by the interval, which is the way that I always say it. So it's the integral from a to b of f of x dx divided by b minus a. The way that they're always going to show it to you on the AP exam is 1 over b minus a integral of a to b f of x dx. So be on the lookout for that. Every time you see that, it's definitely average value. It will always have the same units as f of x. It will definitely show up on table problems. On a calculator, or I mean just in general when you're doing this, if you are approximating the value, make sure that you remember to put the 1 over b minus a, and that you remember to put the approximately equal to sign. The 1 over b minus a in particular, people forget because you get so wrapped up in doing your right sum, your left sum, etc. So it's got to be there. And then my advice would be, if a problem says find the average blah, whatever blah is, could be temperature, it could be weight, it could be whatever, you can rewrite that in your head or on paper as just find the average value of the blah function. So if you're looking for the average temperature, it's the average value of the temperature function. That can make it a little easier to figure out like when to do this process. And in general, as I said before, in your mind, if you see average value, immediately just say, in your head, as soon as you see average value, you should say integral over interval, and you will basically never get it wrong. Okay, let's look at an average value from a table type of problem. So we're given the table, we have x's and we have f of x's. We want to approximate the average value of f of x on the interval from 1 to 7 with a right Riemann sum. So step 1 of this process, you're always going to write down the integral that you're doing. So average value is the integral over the interval. So I'm going to do 1 over 7 minus 1 times the integral from 1 to 7 of f of x dx. Then I'm definitely going to put the approximately equal to sign. I'm going to remember the 1 over 7 minus 1. And then if we're doing a right Riemann sum, our first delta x is 2. We're going to use f of 3. Our delta x is 1. We're going to use f of 4. Our delta x is 3. We're going to use f of 7. So I usually write that down. Then in the next step, I actually sub in values. So I put 1/6, the quantity, 2 times 5, plus 1 times 6, plus 3 times 8. That's where you can totally stop on the AP exam on a free response. I'm going to go one step further and say that that's 40 over 6, or approximately 6.667, 3 decimal places. But you should have stopped on the previous step. The next thing we're going to talk about is how to interpret an average value, which is something they always ask on the free response questions. So remember, it's always going to look like something 1 over 6, the integral from 2 to 8, h of t dt, that kind of thing. As soon as you see that in an FRQ, you know that you are interpreting an average value, approximating an average value, finding an average value. I just put together this table here. We have a function, we have the units for the input, we have the output units, and then the interpretation that you're going to use. So I'll read one of them, and then you can just screenshot this and look at it. So if b of t is our function, the units of t are hours, the output is bacteria. What we would have as our interpretation then is 1/10 the integral from 0 to 10 of b of t dt is the average number, because that's what the integral represents, of bacteria, that's the units of b of t, over the 10-hour period, because we're going from 0 to 10, from t equals 0 to t equals 10 hours. So we want to hit all of the units, we want to explain what that integral represents, and we just want to pull it all together. So the next one, I gave you a temperature function. And then I also gave you a downloads function or something, just trying to keep it kind of current. So make sure that you can do this. It's not very difficult. You just have to be kind of methodical about it. So now I want to talk about the next thing that we're going to do here, which is position, velocity, and acceleration, but this time with integrals. So we've already looked at this before in terms of derivatives. First thing that you're going to find yourself doing all the time is just rearranging the fundamental theorem of calculus. For example, where you end up is going to be where you start, which is x of a plus the integral from a to b of v of t dt. So that's just your start plus your displacement. You can also go the other way and figure out where you started. Where you started is where you ended up minus the integral from a to b of v of t dt. So it's where you ended up minus the displacement. That's a really common thing to do. You definitely got to be able to do that. Another thing that is really important is finding, so displacement is the integral of v of t from a to b. So you're just integrating the velocity function. On the other hand, distance traveled is the integral of the absolute value of v of t dt from a to b. So distance is actually just the integral of speed, right? Because speed is the absolute value of velocity. Now what I want to do is just show you an animation of how you're going to calculate this if you were given the graph of v of t. Okay, so we're going to start off with a piecewise linear graph of v of t, the velocity function. And the first thing that we're going to find is displacement on the interval from 0 to 10 of v of t dt. To do that, we need to find each of these signed regions. And you can see that we're getting 29 over 5, and then negative 62 over 15, and then 8 over 3, and then negative 1/3. If you were doing this by hand, these would be significantly better values. Nice trapezoids, nice triangles, but I wasn't doing it by hand, so it didn't matter to me. So we have all these regions, and for displacement, what we want to do is just sum up the signed areas. All of those total up to 4, which means our displacement is just 4 on the interval. The next thing we'll do is we'll find the distance traveled. So I'm going to actually do this 2 different ways. The first way I'm not going to recommend that you do, but it is what's happening. Distance traveled is the integral from 0 to 10 of the absolute value of v of t dt. So that means we can transform our graph into the graph of the absolute value of v of t dt. Everywhere where negative just reflects over the x-axis. We end up with these regions. Now they're just all positive areas. So you can see we add those up and we get 194 over 15, which again would be a much nicer value if we were doing it by hand. So that is a way that you can do it, but it's not what I would advocate. What I would actually advocate for distance traveled is you take your original calculations where you have some positives, some negatives, and you just add up the absolute value of each quantity. So 29 over 5 already positive, absolute value of negative 62 over 15, 8 over 3 already positive, and then absolute value of negative 1/3. We add up those values, we get the 194 over 15 that we're looking for. This is how you can use a graph of velocity to actually find your displacement and your distance traveled by using signed areas and thinking about absolute values. It's a very common problem. So next up is accumulation in applied context. This is a really big deal. It's very likely to be a free response question, could also appear on multiple choice. If we want to do this, we should start off with the concept of I of t is going to be the rate at which something is coming into the situation, and O of t is the rate at which it's going out of the situation, which makes the overall net rate of change I of t minus O of t. That's an important idea. The total that you end up with is going to be the amount you start with plus the net change, which if we write that as an integral is A of t equals capital A of lowercase a, the amount you're starting with, plus the integral from a to t of I of x minus O of x, the overall rate of change, dx. This is really similar, in fact, to finding position from velocity, right? It's just where you start plus your displacement. It's just in a different context. The values that you get are going to be found using the fundamental theorem, maybe graphically, maybe with a calculator. By the second fundamental theorem, A prime is going to be I of t minus O of t, which is just the rate in minus the rate out. Often on free response questions, you are just asked to find the total amount that came in or the total amount that went out, which means you're frequently on like part A, just integrating I of t, or you are just integrating O of t. Be on the lookout for that. Also, sometimes you are asked if the rate of change is increasing or decreasing, which is really just asking you, is the derivative of the net rate positive or negative? So in that case, you're actually looking at I prime of t minus O prime of t. You're not looking at I of t minus O of t. You will occasionally be asked about I of t minus O of t, but it is more likely on like part D that you're finding the rate of change of the rate of change, really look out for that. So definite integrals are always giving you a net change. If the integrand units are like warbles per hour, the integral units are just going to be warbles, which is something to look out for because they will ask you to interpret this in the context of the problem. If when you do the integral, you get a positive value, that means that overall you gained something. And if you get a negative when you do the integral, overall you have lost something. Here I just have a random FRQ tip, and it is that question 1 versus question 6, there is not any like implied level of difficulty change. But within a problem, it is definitely acceptable for part D to be harder than part A. And I say that because of that, specifically is the rate of change increasing or decreasing question. People get that wrong a lot because they think it's simpler than it is. If you're on part D, it might be more challenging. Okay, the next topic that we want to talk about is also a big one. It's the area between curves, and we're going to talk about it first with respect to x, because with respect to x and y, really the same concept, but it feels very different. So our dx setup is we're always just going to integrate the top curve minus the bottom curve from left to right. If there are multiple intersection points, the top and the bottom can switch. So in that case, you're just going to have to use multiple integrals to find the area. You always want to be doing top take away bottom. On the calculator section, it's actually possible, if you want to, you can do the integral from a to b of the absolute value of the top take away the bottom with respect to x over the region. That will give you the answer, provided your calculator can like deal with it. It's a little more complicated of a calculation for the calculator to kind of deal with. Kind of unfortunately, I don't know, it depends on how you feel about it. This has been on the non-calculator free response question recently, which means you're finding a difference of functions, then you're finding an antiderivative, then you're using the fundamental theorem. And, you know, it's just a lot of work, and it's sort of unbelievable when it shows up there, but it definitely does show up. And while you're doing FRQs, College Board, again, they don't care if the answer is nice or if the answer is ugly. There was one where we had to do it, and we ended up with like a cosine of 2 in the answer, and that just felt wrong, but it was not wrong. So while you're doing it, don't feel that it's guaranteed you've gotten it wrong just because you got an ugly answer. All right, so let's look at an example of this. We're going to find the area between two curves that are going to be integrated with respect to x. So that's a top takeaway bottom situation. So we want the area of the region bounded by f of x is x squared minus 1 and g of x is sine of x. If you look to the side, I've created a graph of this. I've shown a little representative rectangle type deal. Mostly that's where you definitely figure out the top curve and the bottom curve. So in this case, the sine curve is definitely on top and the quadratic is on the bottom. Step 1, we need to know where they intersect each other. We set them equal. We get x1 is negative 0.6367 and x2 is 1.4096. Now we just set up our integral. We're going from left to right, so from x1 to x2 of top takeaway bottom. So one thing you'll notice here is I'm storing the values of x1 and x2, which means in my integral, I'm going to write x1 and x2. I'm not going to write those numerical values. Also, the functions have names, so I'm using the function names. I'm using g of x and I'm using f of x. That's going to prevent you from making mistakes. And in this problem overall, we've gotten approximately 1.6702. We only need 3 decimal places, so 1.670 would be enough. I would say a pretty common question that you're asked about the area between two curves is, can you find a vertical line that splits the region into 2 equal parts? This is not really a trick question. It's pretty easy. Sometimes I ask you to solve it. Most of the time it's just set up because different calculators can definitely do a better or worse job on this thing. What you're going to do is you're just going to go from A to K of top takeaway bottom equals from K to B of top takeaway bottom. There's not really a lot to talk about here, but it is a thing that shows up, so I wanted to cover it and make sure you have seen it. Next up is area between curves, but now you're using dy. So this is the same idea as dx, but instead of integrating top takeaway bottom, you're going to do right minus left because that gives you a positive value when you subtract them. So one thing that you might need to do is switch to functions of y. In fact, you're definitely going to need to do that. So what I have on this slide is just 2 examples of doing that. So I have y equals the natural log of x minus 1 plus 5 and x equals y squared. If you create a graph of this, you see that kind of the best way to do this is definitely dy. So for the leftmost curve, it's already x equals y squared. For the right curve, you actually have to solve it for x. So you're going to subtract 5, you're going to exponentiate, and then you're going to add 1. So you get x equals e to the y minus 5 plus 1. And then I used a calculator. I found the intersection points. The bottom y value is negative 1.001. The top y value is positive 1.009, and then we do the right curve, which is the exponential, minus the left curve, which is just y squared. The other one is just another example of that. Make sure when you're doing right minus left, you put parentheses around the right curve, parentheses around the left curve in case you have to distribute something. But this is all that we're doing. I kind of think that we're overdue for an FRQ where you have to integrate with respect to y, so I would definitely take a look at this before the exam. All right, let's take a look at just another example using dy when we find our areas. So we want the region that is bounded by x equals y squared and x equals y plus 2. Obviously, if the problem is given to you where x equals and x equals, that's a huge tip off that you should be using dy for this problem. Y is actually the independent variable in this case. Step one, I've kind of created a graph just to see what's going on. I've drawn a representative rectangle. I'm gonna take the curves, set them equal. So we have y squared equals y plus 2. That gives us y1 is -1, y2 is 2. I would store those on my calculator, and then my integral is going to be the integral from y1 to y2 of the right-hand curve, which is y plus 2, minus the left-hand curve, which is y squared. Or, you know, if you want to just write it out with a -1 and 2, because those are integers, that's fine. We end up with 9/2. So don't forget, dy means you are using right minus left, and when you find the y bounds, you're always going from the bottom to the top. Next up is volumes with cross-section. So I just recently made a video about this. You should definitely check it out. This is going to be a overview of that, but the graphic comes from it. You need to go into the exam knowing the cross-sectional area formulas for squares, rectangles, triangles, and semicircles. You've got to memorize the semicircles because it's definitely the weirdest one. The setup that you use is just the volume of the solid is the integral of the area formula. So sometimes they'll literally give you the area formula, like they might say the area of a cross-section is, I don't know, 18 sine squared of x. Why is that the area? No one knows. No one needs to know. To find the volume, you just integrate that. And then you could also do this with respect to y, where you're just going from like bottom to top of area as a function of y, dy. Common cross section. So we've got our square cross sections where we're just doing like s squared, and s is top take away bottom in that case. If it is dy, it would be right take away left. We have rectangular cross sections, which is just k times s squared. We have semicircular cross sections, which is pi over 8 s squared. So pi over 8 s squared, you gotta memorize. Equilateral triangles are going to be √3 over 4 and then s squared. And again, that one I think is worth memorizing. For triangles, they may also just describe the triangle to you, like the base is in the region and the height is 5 times the base. So it's just 1/2 base times height. Not really a big deal, but make sure you know that. Okay, the related topic that people are pretty afraid of for absolutely no reason is volume with disks and washers, or volumes of revolution is how I talk about them. We're going to talk about a horizontal axis first because that is by far the most common. So if you're going around a horizontal axis, like for example the x-axis, or y equals -12 or whatever, you're going to use dx. These typically just feel normal, like people want to integrate with respect to x. In any of these problems, the volume formula is going to be pi times the integral from a to b of big R squared minus little r squared, and then dx. The thing that people forget is they definitely forget pi while they're doing these problems. I'm just going to show you the regions, and I'm not even going to do examples. I'm just going to show. If our region falls below the axis, that means that the axis is above. You can see I've drawn a picture. I have both of my curves. I have a big radius and a small radius. In this case, really similar to area, you're going to do top take away bottom. So to find big R, it's top take away bottom, or the axis minus f of x. And then to find little r, you're doing top take away bottom, which is the axis minus g of x. And then we would just shove it into that formula and we would get our volume. You can see here, if the region is above the axis, same exact idea. I've drawn it, I've kind of color coded it. We have a big R and a little r. You're still doing top take away bottom. Every time dx is involved, you're always doing a top take away bottom situation. So big R is top g of x minus the axis, k, and then little r is f of x minus k. And again, we just shove them into that formula and it spits out the volume. Do not forget to write the pi. Do not forget to square them and then subtract them. You'll get the answer every time as long as you recognize this. All right, now let's flip it up. So instead we will do a vertical axis, and the process is almost identical. Remember, for area with dy, we were doing right take away left. Here, to find our r values, our radii, we're going to be doing right take away left. Around a vertical axis, you're going to be using dy. I don't know why I wrote usually. You're always going to be using dy. Our volume formula is still exactly the same, except now we have y bounds instead of x bounds. So it's pi, the integral from c to d, big R squared minus little r squared, and then dy. If you look at our region, to the left here, the region is to the right of the axis. So big R is going to be right take away left, or n of y minus k. And our little r is going to be the left curve minus the axis. So that's m of y minus k. So it's really the same setup. You're always just trying to get a positive r value. So that's always going to be right take away left dy or top take away bottom dx. If you look at the other graph, you can see big R, because the axis is to the right, is now just the axis minus that outer curve, so m of y. And then little r is the axis minus that closer curve, which is n of y. You set it up, you shove it into the volume formula, it spits out the answer. Again, don't forget pi. All right, if you're in Calc AB, you're actually done reviewing at this point. Go do FRQs or multiple choice, or just chill out. If you were in BC, we've got more to do. First up, we have the arc length function. So arc length is going to be the integral from a to b of the square root of 1 plus f prime squared dx. There's a couple of typical questions that you're asked about this. The first one is they will ask you for the perimeter of a region. Sometimes they will ask you to identify the correct integral from a selection of 4 choices. Sometimes you have to find the function that was involved in finding the arc length. And occasionally you have to approximate arc length with a sum, like a right sum or a left sum. Okay, let's take a look at our first example here. We want to find the perimeter of the shaded region. So our curves are 3/2 quantity x minus 1 squared minus 2, and also sine of x plus 3. So those are our 2 curves. First thing we need to do is we need to figure out where the quadratic intersects the x-axis. I'm going to call that point A. I use a calculator. I got A is approximately 2.155. We need to figure out where the quadratic and the sine curve intersect, because that's another x-coordinate that we're going to need. So I set those equal. I got B is approximately 2.873. Now, we need to deal with the arc length along the sine curve, right? So the arc length along the sine curve is going to be the integral from 0 to b, because the sine curve is the blue curve there. So it's the integral from 0 to b of the square root of 1 plus the derivative of sine plus 3 is just cosine, and we are squaring that, so it's square root of 1 plus cosine squared of x dx. That's the first part of the perimeter. Then we need to deal with the part of the quadratic that is between a and b. So that's going to be the integral from a to b, the square root of 1 plus the derivative of 3/2 quantity x minus 1 squared minus 2, which is just 3 quantity x minus 1. So we have the square root of 1 plus the quantity 3 quantity x minus 1 squared. That's annoying to say. Now, when you're doing these problems, the most common mistake I see my students make is they actually just forget the horizontal and vertical segments that are making up the perimeter here. So from the origin to A is a part of the perimeter, so that's actually just a length of A. And then also from the origin up to that y-intercept, which is 3. So we need to include those as well, and that's how we would do this problem. All right, let's look at another kind of classic arc length problem. So we're given a table of values. We want to use a right Riemann sum with 3 subintervals to approximate the arc length of f of x on 0 to 6. So our subintervals are definitely going to be from 0 to 2, from 2 to 3, and from 3 to 6. And since we're doing a right Riemann sum, we're going to be interested in values at 2, and then at 3, and then at 6, the right endpoints. Arc length in general here is just going to be the integral from 0 to 6 of the square root of 1 plus f prime squared dx. So what we need to do is a Riemann sum for this new function, square root of 1 plus f prime squared. So our first delta x is 2, and then the right endpoint of that is the square root of 1 plus the quantity 1.1, which is f prime of 2 squared, plus our delta x is 1, and the function value is the square root of 1 plus the quantity 1.6 squared, because 1.6 is f prime of 3. And then our delta x is 3, and we have the square root of 1 plus the quantity 2.0 squared, because the value of f prime of 6 is 2. And that's really all we would do here. So finally, I have one more example that I want to do, and it's just arc length, where we first identify f prime, and then we use that to figure out what f is actually equal to. So our question would be the integral from -1 to 3 of the square root of 1 plus x to the 6 dx represents the arc length of a function on -1 to 3. If f of 2 is 7 and f prime of x is greater than or equal to 0, we want to find f of x. So for the solution, first thing we do is we look at the integrand and we recognize this is an arc length integral. So the square root of 1 plus f prime squared, which is the square root of 1 plus x to the 6th, kind of tells us that f prime squared is x to the 6th. So that means that either f prime is x cubed or negative x cubed. Since the problem says that f prime is greater than or equal to 0, that tells us that f prime is positive x cubed. I'm thinking about it now, this is like a slightly more complicated question, but let's not worry about that at the exact moment. Let's just carry this through. F of x is the antiderivative of that, which is x to the 4th over 4 plus c. Then we are told that we go through the point 2, 7, which means 7 is equal to f of 2, or 2 to the 4th over 4 plus c is equal to 7. C must be equal to 3. And then our function works out to x to the 4th over 4 plus 3. The more I think about this problem, the more I think on a real AP exam it would be phrased better so that you could clearly identify which derivative to grab. But you know what? It's the idea that matters. So, all right, let's move on to Unit 9. Okay, Unit 9 is all about parametric, vector, and then polar functions. So let's see what we can do. So parametric vector functions, the absolute basics. Your position is going to be given by x of t, y of t. I would say the AP exam makes almost no distinction between parametric and vector, which is why I'm kind of grouping them together. There are a lot of rates of change involved here. So you could have x prime of t, which is dx dt, or y prime of t, which is dy dt. I kind of think on the modern version of the exam that if they give you dx dt, you should just make a statement, let x prime of t equal dx dt, so you can work with x prime. The notation is a little easier to deal with. These derivatives, dx dt tells you if you are moving to the left or to the right because it's the rate of change of x. Dy dt tells you if you're moving up or down. So sometimes you'll talk about x increasing or y increasing. For a particle to be completely at rest, you would need dx dt to equal 0 and dy dt to equal 0. The slope of the tangent line is still dy dx, but in this case, when you find dy dx, you're just going to be doing y prime over x prime. And I think that when you are finding dy dx, the first thing you should do is write down it's y prime over x prime, and then you find the slope, because it's not really obvious that that's what it is. Now let's talk a little bit more about the tangent line to a parametric curve. So the tangent line at t equals a is going to be y minus y of a equals y prime of a over x prime of a, which is just the slope, quantity x minus x of a. So notice t is not actually involved there. The most common mistake that I see people make is they use t instead of x in the equation. So find your ordered pair, write it down, and you will probably screw up less often. Another thing that occasionally comes up, I can think of like one FRQ where it definitively came up, and every year when we review it, it's a little tricky for people. The angle between the tangent line and the x-axis, or really any horizontal line, is theta equals the inverse tangent of dy dx. So we're going to have to deal with that. That's also just the inverse tangent of the slope. So if you know y equals mx, it's the inverse tangent of m. And again, don't confuse t equals a with x of a. In the tangent line, you have to use x of a. Classic mistake. All right, let's talk about velocity, speed, distance, and arc length. The velocity vector, whether you're given parametrics or it's said to be a vector equation, it doesn't really matter. This is what you're doing for velocity. Velocity vector is r prime of t, or usually you don't even name it. You could just call it v of t, in fact. V of t is the derivative of position. So I do think if your position is called s of t or r of t, you should start out with r prime or s prime of t, but then it's just dx dt comma dy dt. And we write them as ordered pairs on the AP exam, and that's totally fine. Your acceleration vector. So acceleration is the derivative of velocity. So I think you should start with a of t is v prime of t. And then that's just your second derivative, comma, your second derivative. Speed is the magnitude of velocity, or the square root of x prime squared plus y prime squared. Don't confuse speed and acceleration. I don't think anyone does, but I think College Board thinks that you do, because they frequently make one section of an FRQ to find the speed at a time and then the acceleration vector at that time. I don't know why they do that. Distance traveled is just arc length. So distance traveled and arc length are actually the same thing. So I'm going to cover them both at the same time. It's the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt, which you'll notice is just the integral of speed. That's exactly the same thing as one-dimensional motion, right? You would do the integral of the absolute value of velocity. Here we're doing the integral of the magnitude of velocity. And as I mentioned, I think that if you're going to use x prime of t and y prime of t, but they gave you dx dt and dy dt, that you should actually write down a kind of let statement. Let this equal this, let this equal this. So let's talk about how we can find position from the velocity, which is definitely a thing that you're going to be asked to do. They typically will just give you the position at like t=5 and they'll ask you for either the x coordinate at 2 or the total position at 10, something like that. This is exactly the same as what you did in Calc AB when you had velocity and you wanted position on like the x-axis or just the y-axis. So if you're going to move forward, x of b, y of b, your final position is where you started, which is x of a, comma, y of a, and then you're going to add each displacement. So you're going to add the displacement of x, which is the integral from a to b of x prime of t. You're going to add the displacement for y, which is the integral from a to b of y prime of t. The way I read that is really weird, so I'm just going to say it again. It's x of a, where you started, plus the displacement for x, comma, y of a, where you started, plus the displacement for y. We can go backwards in the same way. So if you want to find where you started, which would be x of a, comma, y of a, it's going to be where you ended for x, so x of b, minus the displacement from a to b, so minus the integral from a to b of x prime of t, and then the same thing is true for y. So just pay attention to what they're asking for. One thing that I see a lot of people get wrong, which is kind of a sad mistake, is everyone just assumes that it starts at t=0. Make sure you reread the problem right before you set up your integrals because it doesn't always start at 0. I will say they also sometimes give different representations, so maybe they'll give you the actual graph of x, but then they'll give you a table of values for y prime, and they ask you to do like a Riemann sum to figure out the y value, and then you just have to read a graph for x. Any number of combinations there could occur. We know how to deal with all of those, so it's not really a big deal. Okay, now we're just going to do an example that covers almost everything I think you would run into. So we are given that v of t is 3 cosine of pi t, comma, e to the t over 3, and the position at t=3 is 8, comma, -3. So notice that's the position at t=3. First up, if we want the speed at t=2, that's going to be the square root of x prime of 2 squared plus y prime of 2 squared. Grab a calculator. I got 3.577. I checked these answers once, so let me know if these aren't right. The acceleration vector at t=3.5 is a of 3.5, which is v prime of 3.5. If this was calculator, you could just now write down, so I got 9.425, comma, 1.070. If it was non-calculator, you can do it by hand. It's just not all that much fun. Actually, it's pretty easy to do by hand. All right, distance traveled on the interval from 0 to 3 is the integral from 0 to 3 of the square root of x prime squared, so that's 3 cosine of pi t squared, and then y prime squared, so quantity e to the t over 3 squared, and that's approximately 8.045. If we want to find the position at t=2, well, then we need to do where we are at t=3 and subtract the displacement. So that's going to be 8 -3 is the ordered pair at t=3, and then minus, we've got these integrals here. This is kind of a weird way of showing the work, but it's what I chose. I got 8 for x and I got -5.312 for y. If we want the position at t=4.5, we're going forward this time. So last time t=2 was less than t=3, so that's why we subtracted. Here we're going forward, so it's where we are, r of 3, plus the integral from 3 to 4.5 of v of t dt, and that gives us approximately 8.955, comma, 2.290. If we want the tangent at t=2, step 1 I would say is we need to find dy dx, which is y prime of 2 over x prime of 2. I got approximately 0.649. We need the ordered pair, which we found previously was 8, comma, -5.312. And then our tangent line is just a normal tangent line. So it's y minus the y value equals the slope quantity x minus the x value. So that's basically everything they really ask you. So let's move on to the next thing. The second derivative of a parametric set of equations is genuinely kind of a weird thing. So I recommend this is one of those things you definitely memorize. It is actually just the chain rule, but it doesn't really feel like it. So the second derivative is going to be d dt of dy dx. dy dx is going to be a function of t. That's why we're finding d dt of dy dx. And then we're going to divide by dx dt. So if you were going to say it out loud again, it's the derivative of dy dx with respect to t divided by dx dt. There's nothing really complicated about it. It's just like a weird formula. I've never seen this on an FRQ, but it does come up on multiple choice questions. All right, I think this is worth doing an example of. So if we want to find the second derivative for the parametric curve x equals t squared and y equals t cubed, step 1, we need to find the first derivative, which is dy dx. So that'll be dy dt over dx dt. dy dt is 3t squared, dx dt is 2t, so we have 3t squared over 2t, which gives us 3 over 2 times t. Now to find the second derivative, we take the derivative of what we just got with respect to t, so that's the derivative with respect to t of 3 over 2t, which is just 3 over 2, and divide that by dx dt, which is 2t, so we end up with 3 over 2 over 2t, or 3 over 4t. It's just weird, it's not really bad. Now let's talk about polar coordinates, the other topic that's in this unit. So polar coordinates, we need to know the common polar curves. The vast majority of polar curves that you're given are of the form r is equal to some function of theta. The common polar curves, I think you should just look at on Desmos or on your calculator or something, get familiar with them, make sure you kind of understand how they work. So here are a bunch of sine curves you should look at. We got some circles, we got some rose curves, and some limicons, and also cardioids. And then I have cosine versions. I'm not kidding. Go to Desmos, type them in, see what they look like. Also, the most famous polar curve is certainly r equals a constant, which is just a circle centered at the origin. When you are looking at them, I would say focus on what is the interval of theta on which this thing is traced out, because that's going to be important when we're trying to find areas. And then another famous type of polar curve would just be a line through the origin, which is theta equals pi over 3 or pi over 6. It'll probably be a unit circle angle, but who knows, it could just be theta equals the inverse tangent of something, right? The inverse tangent of the slope of a line. So I probably should have added in the last frame, I have tons of videos on how to deal with polar. There's a lot on how to graph famous polar curves. There are separate videos on finding polar areas that are very popular. And I have an entire other Unit 9 review video if you want to go seek that out. Let's continue talking about polar coordinates. We need to know how to convert from polar to rectangular using the equations x equals r cosine theta and y equals r sine of theta. So you're going to replace that r there with the polar curve. So if the polar curve is 5 cosine of 3 theta, it's going to be 5 cosine of 3 theta cosine theta, and then 5 cosine of 3 theta sine theta. You're basically just turning polar into parametric equations, actually. You might be asked, they ask a lot of basically like pre-calc questions about polar. You might be asked to find like when is x equal to 12? If that's the case, you just set r of theta, cosine of theta, equal to 12 and you find theta. That's all it is. That's been on the FRQs before. If you want to talk about a polar curve moving left, right, or up, down, you're just going to look at dx d theta and dy d theta. I don't know if this is just in review books or if it's actually on the exam. I cannot remember right now. But sometimes I've seen questions where they talk about position relative to the x-axis, like are you approaching it or moving away from it, etc. In that case, you would also need to know the y-coordinate or the x-coordinate to know if you're like above the x-axis and dy d theta is negative, or if you're below the x-axis and dy d theta is negative. So you might need to combine a bunch of rates of change for that sort of thing. The slope of a tangent line is still dy dx, but remember we basically wrote it as parametric, which means that's y prime over x prime, and we just wrote y as r of theta sine of theta, so that's a product rule, and we wrote x as r of theta cosine of theta, so that's also a product rule. So you find yourself using a lot of product rule. Let's talk about interpreting dr d theta. So there's just a lot of d whatever d thetas involved. There's dx d theta, dy d theta, dy dx, which is not really d theta. And then there's a dr d theta. So dr d theta tells you the rate of change of r, which is the signed distance from the origin. So r might be positive or negative. Dr d theta might be positive or negative. And their interaction will tell you the relationship to the motion of the particle and the origin. So if r is greater than 0 and dr d theta is greater than 0, you're moving away from the origin. If r is greater than 0 and dr d theta is less than 0, you're moving toward the origin. On the other hand, if r is less than 0 and dr d theta is positive, then you're moving toward the origin. And if r is less than 0, dr d theta is less than 0, you're moving away from the origin. So you might have noticed while I was saying all this is exactly the same thing that happens with speed, right? If velocity and acceleration have the same sign, then speed is increasing. If they have opposite signs, then speed is decreasing. In this case, if r and dr d theta have the same sign, you're moving away from the origin. And if they have opposite signs, you'll be moving toward the origin. They don't ask about that all that often, but it's definitely a fair question, so we should know how to do it. I would say that polar area is the thing that gives people the most nightmares about polar, and I don't really think there's a reason for it. I think it's that people aren't really well acquainted with graphing polar, and that's really where the issue comes from. The formula, though, does have two places that you can make a very common mistake. The area of a polar region is 1/2 the integral from a to b. Those are the theta values where you start and then stop the region of r squared d theta. So it's 1/2 the integral of r squared d theta. You can probably guess the two mistakes people make. They forget the 1/2 and then they forget to square r. Those are the two things. So make sure you don't do those. Here's a picture of a polar region, and I've included theta equals pi over 6 and theta equals pi over 3. So if we wanted to find the area of this region, we would just set up 1/2 the integral from pi over 6 to pi over 3 of the quantity 2 plus theta cosine 3 theta squared d theta. So there's a lot of places you could screw up typing that in. Make sure you put r in parentheses so that when you square it, you're truly squaring everything. Otherwise, I think what we should do is look at how some polar curves are traced out so that we can see where the bounds would come from. And then I would encourage you to seek out my other graphing polar videos. They will give you a lot of insights into how this works, but we're going to do this with an animation. Okay, so we're going to start out and we are going to graph r equals cosine of 3 theta. And the thing we're interested in is the area of this petal right here. So to do that, we have to figure out what values of theta generate that petal. The way that we're going to deal with that is we're going to look at the rectangular graph and we are going to figure out where the petal comes from. So what I want you to focus on when you're looking at the rectangular is how does the rectangular graph correspond to the polar graph? Because if we can find the region on the rectangular graph that is creating the polar graph, all we need to do is take the bounds from the rectangular graph. I basically do all polar area problems by creating a rectangular graph, finding the corresponding region, stealing the bounds, and in this case we can see it's negative pi over 6 to pi over 6, and then writing the polar area. So the areas are not the same. You can't just do the integral of the rectangular curve. You do have to do the polar integral, but it will give you the correct answer. So we use rectangular for bounds, and then we use polar for area. And you can see those are our integrals. I just want to show you how this would work with another curve. So 1 minus 2 sine of theta. If we want to do that inner loop, we look at the rectangular graph and we see where on the rectangular graph we are generating the inner loop. And you can see it's from pi over 6 to 5 pi over 6. So when we set up this integral, it will be 1/2 the integral from pi over 6 to 5 pi over 6, and then the quantity 1 minus 2 sine theta squared. Another thing that they might ask you to do with polar areas is to find the area between polar curves, because why not? So for this one, we need to figure out which polar curve is farther from the origin, because that will give us a larger area. And then obviously another one is closer to the origin. So when we do this, we're basically just finding a big area minus a little area, which is a totally fine way of doing it, and that will get you the answer. But we can combine them into one integral, and that integral will be 1/2, because polar area just has a 1/2. The integral from a to b, so that's where theta is starting and where theta is ending. And then I'm saying that r2 is bigger than r1, so it'll be r2 squared, that gives me my big area, minus r1 squared, which gives me my small area, and that's the whole thing. You might look at that and say, this reminds me of volume. It reminds me of volume as well. It's basically the same idea, except instead of a pi in front, you have a 1/2 in front. Keep that in mind, file it away. You're always just doing big area minus little area. So here is a polar region. I've got r1 is sine of theta, r2 is 2 plus cosine of theta, and we're on the interval from 0 to pi over 2. So if we wanted to find the area between these things, what we would have to do is 1/2 the integral from 0 to pi over 2 of the one that's farther out, so the quantity 2 plus cosine of theta squared, minus the one that's closer in, which is sine of theta. So it's minus the quantity sine of theta squared d theta, and that will give you the answer. That would almost certainly be set up but do not evaluate, or it would just be a calculator question. I do just want to take a second to talk about splitting a polar region into 2 equal parts. It's about as simple as it seems like it should be. If the line theta equals k splits a polar region in half by area, then you're just going to use intervals for your integrals of a to k and then k to b. On the other hand, if the line y equals mx splits a polar region in half by area, you're going to end up using k is the inverse tangent of m. So that'll be the upper bound of the first integral and the lower bound of the second integral. And if you look, I have an example here. R1 and R2 are those things that are written over there. And we're stuck between pi over 6 and 2 pi over 3. So the setup, because we have named our functions, I'm just going to use the names. R2 is farther out, and you can kind of work that out because 1 plus 0.8 is definitely bigger than 0.45 plus 0.25. We're going to set up 1/2 the integral from pi over 6 to k of r2 squared minus r1 squared is equal to 1/2 the integral from k to 2 pi over 3 of r2 squared minus r1 squared. I do not think they would make you solve this, but if you did solve it, I think that you would get 0.992. The thing that I want to caution you about is sometimes when I'm doing rectangular areas and splitting them in half, I will do the integral from, I don't know, a to k is equal to 1/2 of the integral from a to b. So I'll do half of the area is equal to half of the total area rather than doing 1/2 and then the other half. With polar, be really careful with that because you already have a 1/2 in front of everything, so it's a little deceptive what you're doing there. I would always just split it into a to k and then k to b. A final polar topic that we definitely need to talk about is related rates in relation to polar, because although that's not strictly a polar thing, on the polar FRQs, they almost all the time ask a related rates question. So what they will tell you is that r is a function of theta, that's your polar curve, and then they just tell you that theta is a function of time, and they usually tell you d theta dt is, I don't know, 15 or something. They just give you a value for it. So what I want you to know is, in that scenario, we're just going to kind of chain rule our related rates. We'll say that dr dt is dr d theta times d theta dt. dx dt is dx d theta times d theta dt. But remember, x is r of theta cosine of theta, so you're going to use the product rule for dx d theta. dy dt is similarly dy d theta times d theta dt, and y, unfortunately, is also going to require a product rule. So these come up almost every time there's a polar question, a polar FRQ, I should say, so I did want you to be aware of it. They're not hard, they're just kind of like, what are we doing type situation. Why have we thrown this in? Okay, so let's finish talking about polar here with a related rates example. We've got a particle moves along r equals 2 plus 3 cosine of theta with d theta dt is equal to 0.4 radians per minute. So what we're going to do is we're going to find dr dt, dx dt, and dy dt. And so I'm just going to kind of show you the work. dr dt, we have dr d theta times d theta dt. dr d theta is just -3 sine of theta, so we plug in pi over 4. Then d theta dt is 0.4. We multiply them, we get about -0.849. For dx dt, I don't think you'd have to do it by hand, but if you did, x is r times cosine of theta. So dx d theta is first derivative of the second plus second derivative of the first, but if you rearrange it so that you don't have a negative leading coefficient, you get dr d theta times cosine minus r times sine. Then you have to do dx dt is dx d theta times d theta dt. I would just use a calculator to find dx d theta. I think this would be calculator. I got approximately -1.766. Finally, dy dt. So to find dy d theta, we have to use the product rule because y is r times sine of theta, so it's first derivative of the second plus second derivative of the first. And then to find dy dt, it's dy d theta times d theta dt. Calculator, again, just substitute in. I got approximately 0.566. So I think that's it for polar. Next up, Unit 10. Okay, so Unit 10 is all about series, what we've all been waiting for. We're going to start off with geometric series. A geometric series is the sum from 0 to infinity, or whatever starting point to infinity, of a times r to the n. So you get a plus a times r squared, etc. forever. A geometric series will have a sum of what I usually say is the first over 1 minus the ratio, but here we have a over 1 minus r, provided that the absolute value of r is less than 1. So this will always converge if the absolute value of r is less than 1. It will always diverge if the absolute value of r is greater than or equal to 1, which means there's no point in testing the endpoints for convergence. If r is less than 0, you're definitely going to get an alternating series, which is a big deal. So as I mentioned, think of that sum as the first term over 1 minus the ratio. That'll prevent you from making a mistake if it starts at 0 versus 1 versus 2, etc. Another thing that's a little bit weird, but I think is worth saying is pi is bigger than e, which means that e over pi is less than 1 and pi over e is greater than 1. Sometimes in like multiple choice questions, they'll just throw that in as the ratio, and you have to be aware of that. And let's just quickly look at some examples of geometric series of constants. So you might see from 0 to infinity, 5 quantity 2/3 to the n. That means that r is 2/3. This definitely converges because r is less than 1. And our sum will be the first term, which is 5 over 1 minus the ratio, so we get 15. The next one alternates, so we have 4, the quantity -1/2 to the n. r is -1/2. The absolute value of that is less than 1, so this converges to the first term, what you get when you plug in 0 over 1 minus -1/2, so we get 8/3. The next one, we have 7, the quantity 5/4 to the n. r is equal to 5/4, that's bigger than 1, so we just diverge. And then the next one is one that you have to look out for, so it's the sum from 1 to infinity of e to the -3n. So that's e to the -3rd to the n, which means that our ratio is 1 over e cubed. Basically, and 1 over e cubed is definitely less than 1, so this does converge. Our first term is what we get when we plug in 1, right? So that's e to the negative third. So the sum is e to the negative third over 1 minus e to the negative third, which you can simplify, they probably would on multiple choice, to 1 over e cubed minus 1. I also think it's really important to take a look at geometric series that are functions, so they're going to have x in them. You might see something like the quantity x minus 1 over 3 to the n, or 2 quantity negative x over 4 to the n, or that third one. So when you're dealing with these and you have to figure out what r is, what you want to do is group everything that is raised to the nth power in one set of parentheses. Once you've done that and everything to the n is in one set of parentheses, that's r. The sum is definitely still just the first term over 1 minus the ratio, which means you kind of end up with rational functions for the most part. The convergence is exactly the same. So you need the absolute value of whatever you just got for r to be less than 1. It is never going to converge at an endpoint. And when we talk about an interval of convergence, which we will talk about, that's basically just the domain of the sum. Like, it doesn't make sense to use the sum outside of the interval of convergence, but on the interval of convergence, it's exactly the same as the series, provided you go to infinity. So let's just look at some examples of what we can do with geometric series that have x in them. So we have this thing, it's negative 1 to the n, quantity x plus 2 to the n over 2 to the n. You can see there's a lot of things to the n. So step 1 is bring them all under one set of parentheses. So we get the quantity negative x plus 2 over 2 all to the n, which means that r is negative quantity x plus 2 over 2. So this will converge anytime r, or the absolute value of r I should say, is less than 1, which means that you can multiply by 2 and then you're centered at negative 2 and you can go 2 in either direction. So from negative 4 to 0, that's our interval of convergence. The sum is 1 over 1 minus the ratio, which is going to be 1 over 1 minus the quantity negative x plus 2 over 2, which simplifies to 2 over x plus 4. And then we want to state that interval again, so negative 4 to 0. And you can see I just did a couple more. I think that they're all interesting. So you can see for the second one, because it's the n plus first power and not just the nth power, our first term is actually, when we plug in 0, it's the quantity x minus 3. So when we go down there and we do our sum, the first thing in the numerator is x minus 3. And then 1 minus the quantity x minus 3, which just cleans up a little bit, and then we state our interval. And then for the third one, we have x to the 3n plus 1, which means it's really x times the quantity x cubed to the n. So r is x cubed. That's going to converge if the absolute value of x cubed is less than 1, which means the absolute value of x is less than 1. And our sum is the first term, what we get when we plug in 0, which is just x over 1 minus the ratio. Okay, for geometric series, it's easy to tell if you converge or diverge. It's just about the absolute value of r. The nth term test for divergence is a really important test. It just says if the limit as n approaches infinity of a sub n is not 0 or doesn't exist, then the sum from 1 to infinity of a sub n diverges. So this test can only prove divergence. You cannot show that something converges by using this. If the limit as n approaches infinity of a sub n is equal to 0, there's absolutely no conclusion that you can draw. For example, to show that something diverges, we would have from 1 to infinity 3n plus 1 over n plus 2. That definitely diverges because the limit of the nth term is 3, which is not 0. I just want to throw in a classic example here of the sum of the quantity 1 plus 1 over n to the n. That's going to diverge because the limit of that nth term is actually e. It is not equal to 0. The main takeaway here is that this can only tell you if something diverges. It cannot tell you if something converges. The next test that we want to talk about is the integral test, and the integral test is going to tell you for the sum from 1 to infinity of a sub n, where a sub n is equal to f of n, if f is positive, continuous, and decreasing. So those are three criteria: positive, continuous, decreasing. For x greater than or equal to some value n, then the sum from n to infinity of a sub n and the improper integral from n to infinity of f of x do the same thing. They either both converge or they both diverge. So when you look at that, you know you're going to have to do an improper integral, and you're going to have proper notation, and also possibly you're going to have to show that a function is decreasing. I mean, I think you can almost always just assert that the function is positive and continuous on the interval. Often it is the case, or I would say maybe always it's the case, if you have to use the integral test, they either expressly tell you to use the integral test, or like part A will be to show that the function is decreasing on some interval or from n to infinity, and then you kind of just go with it. I would never choose to use the integral test if I had any other option. Let's take a look at an integral test example. So we're going to do the sum of n over e to the n. So we have that sum, and we're going to say a sub n is equal to f of n, where f of x is x over e to the x, or x e to the negative x for the purpose of taking derivatives. Clearly, if we're going from 1 to infinity, then f of x is positive. What we really need to worry about is f of x being decreasing. I found f prime using the product rule, and then I factored f prime, and f prime is definitely less than 0 every time that x is greater than 1, because the sign of f prime is just determined by 1 minus x. So we know that f is decreasing for x greater than 1. The next thing we have to do is our improper integral. So we're going from 1 to infinity of x over e to the x dx, which is going to be the limit as b approaches infinity of the integral from 1 to b of x e to the negative x dx. We have to do integration by parts on this thing, so we end up with limit as b approaches infinity of negative x e to the negative x minus e to the negative x from 1 to b. It's really the improper integral that's the pain in the neck here. And then we take the limit as b approaches infinity, which leaves us with just 2 over e, which is a finite value, so this converges. Since the improper integral converges, we know that the summation or the series also converges by the integral test. That's why I would not do the integral test unless someone forced me to do it. Now let's talk about the harmonic series. So the harmonic series is just the sum from 1 to infinity of 1 over n, which is just the sum of the reciprocals of the integers. So 1 plus 1/2, 1/3, 1/4, etc. This series famously diverges. In fact, it's kind of the dividing line between series that converge and diverge. So you do want to know it. And also you can cite it as your justification on a series question. So I would say when you're doing the ratio test, which we'll get to eventually, often one of the endpoints will give you the harmonic series. So you just say diverges, harmonic, and move on. Any constant multiple of this series will also diverge. So if you have a 3 over n or an 8 over n, you know that you're going to diverge. After harmonic, you definitely need to talk about p-series, because p-series are the series that the harmonic series divides. So a p-series looks like 1 over n to the p, and this will converge if p is greater than 1, and it will diverge if p is less than or equal to 1. If p is equal to 1, you actually just get the harmonic series. I look at this and I think this is actually the easiest of the series tests, because you kind of just look at it and think, oh, p is this or p is this, converges or diverges. So here are 3 examples. 1 over n to the 3/2 converges, p is 3/2 greater than 1. If you have 1 over the 5th root of n squared, that's the same as 1 over n to the 2/5, p is equal to 2/5 less than 1, diverges. If you have n to the negative 4/9, that's 1 over n to the 4/9, p is 4/9 less than 1, diverges. And then a kind of classic thing that they might ask you to do is to find a value of p such that it does converge, which I always think is a little mean, because it's called a p-series and then they'll use p as the variable in this, but whatever. So we have 1 over 3 to the p. If we want this to converge, we need the exponent 3p to be greater than 1, which means we just need p to be greater than 1/3. You're going to use p-series a lot in comparisons and testing endpoints. Now let's take a look at the first of the 2 comparison tests. So that's going to be the direct comparison test. Direct comparison, we need a sub n to be greater than 0 but less than b sub n. So a sub n is the smaller series and b sub n is the larger series. From that kind of logic, if b sub n, the bigger series, converges, then a sub n must also converge. If a sub n diverges, then something bigger than that, so the sum of b sub n, must diverge. That's basically what the comparison test says. I would honestly never use this given the option. This is up there with the integral test. I'd actually rather do the integral test. They really like to set you up to just use this on multiple choice questions rather than free response questions. So you'll see questions like a sub n is bigger than b sub n, which of the following must be true? And then it's like, if a sub n converges, then b sub n must converge. If a sub n diverges, you just wouldn't know anything in that scenario. So you do want to work out kind of the 4 possibilities, like a sub n is bigger or a sub n is smaller, and then each of them can either converge or diverge, and just think about what happens in that scenario. But you will probably see this in multiple choice, if at all. Now let's talk about limit comparison. This is one that I enjoy using. So ratio test, limit comparison test are my favorite to use. Integral test, direct comparison, least favorite. Limit comparison says if a sub n and b sub n are greater than 0, so you need positive term series, and the limit as n approaches infinity of a sub n over b sub n is L, where L is positive and finite. So those are the requirements. It has to be positive and finite. Then a sub n, the sum of a sub n and the sum of b sub n just do the same thing. They either both converge or they both diverge. This is what you're doing in your head when you say, this just looks like this this series and that series converges, so this one must converge. That kind of logic. When you're doing this, what you want to do to find the series to compare it to is just reduce down the series that you have to the simplest possible version of itself, and we're going to look at that in a second. You do end up with a lot of p-series and a lot of geometric series when you're doing this. This is one that you might find yourself using to test endpoints, or just on like a multiple choice question where they say, you know, which of the following converge or diverge. You look at them, you'll say I could compare it to this, and therefore this is true. So here are 3 pretty quick limit comparison examples of kind of how I do them in my head. So I'm not actually showing the work here, but if we have 2n squared plus 5 over n cubed minus 1, I look at that and I think that's basically 2n squared over n cubed, which is just 2 over n, and then 2 over n would diverge because it's a p-series where p is 1, which means that the original series must also diverge. If I'm properly using the limit comparison test, I would say the limit as n approaches infinity of the original over the comparison is just going to give me 1, which is positive and finite, therefore they both do the same thing. On the next one, it's 1 over the square root of n squared plus 4n. You just discard the 4n and you say that's basically 1 over the square root of n squared, which is 1 over n, and that's the harmonic series, so that's going to diverge. And then for the last one, you would look at it, you kind of ignore the 1 and you say it's 1 over the square root of n to the 4th, which is basically 1 over n squared. That's a convergent p-series, which means I could limit compare this to 1 over n squared and I would get positive finite, which means they do the same thing. So this one converges. It's really the best test. I mean, it's super fast. You can just look at things and know that they converge or diverge, and if you had to justify them, you would use the limit comparison test. Now we want to talk about the alternating series test, or AST. The statement of it: if the sum from 1 to infinity of -1 to the n b sub n, or -1 to the n plus 1 b sub n has the following 3 things true: b sub n is greater than 0, b sub n plus 1 is less than or equal to b sub n, and the limit as n approaches infinity of b sub n equals 0, then we know the series converges. Now on the solutions that they release from previous FRQs, it always just says the terms are alternating and decrease in magnitude to 0, therefore the series converges by AST. So that's what we're going to say. Memorize that sentence. The terms are alternating, decrease in magnitude to 0, therefore the series converges by AST. Alternating series error is definitely something that you will be asked about. It frequently shows up on the released free response questions, so we definitely know it's on the exam. The error just says if you use n terms to approximate a convergent alternating series, the error is less than the magnitude, or the absolute value, of the n plus first term. So this is the easier of the 2 types of error that you're going to have to deal with, so you kind of hope that it's an alternating series. If you are not expressly told to use it, what I would say is, if you're talking about error, first say that you have a convergent alternating series, because otherwise why are you using the alternating series error? If you're not told to use Lagrange error, I would say 9 out of 10 times it's definitely the alternating series error, so be on the lookout for that. I do want to make sure that you're really on top of this, so I'm going to show a little animation of how to do this. Okay, so we're going to start off and we're looking at the sum from 1 to infinity of -1 to the n plus 1 quantity x minus 2 to the n over 2n minus 1. So that's a function of x. It's going to converge for some values, it's going to diverge for other values, potentially. We would have to check that. But what I want to do is show you how to use alternating series error. What we're going to do to investigate this is we're just going to look at f of 3. F of 3 is a convergent alternating series because the terms alternate and they decrease in magnitude to 0. So to find the error, we can use the alternating series error bound, and that error is going to be less than the magnitude of the first term that we have left off. Let's take a look at what that really means. So to start with, we just want to see what the terms are, right? So I'm plugging in 1 and then 2 and 3 and 4, etc. So I get 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. Now we need to investigate convergence. So what we'll do is we'll say if we only use the first term to approximate the sum, well then we think the sum is 1, and our error is this first term left off, so 1/3. If we use the first 2 terms, we get 1 minus 1/3 as our approximation, and the error would be, at most, 1/5. It's actually less than 1/5. If we use 3 terms, we think our sum is 1 minus 1/3 plus 1/5, which would make our error less than 1/7. No matter what you do, the error is the magnitude of the first term left off. Now let's get into the ratio test. So this is another big one. This and the limit comparison tests are what I would choose to use all day if given the option. So the ratio test says if we have the sum from 1 to infinity of a sub n might be positive, might be negative, might be alternating. It does not matter. The ratio test doesn't care. We're going to let L equal the limit as n approaches infinity of the absolute value of the n plus first term divided by the nth term. So you always are going to have to take a limit to use the ratio test, but the limits are pretty predictable when you do this. The conclusions: if L is less than 1, the series converges absolutely. If L is greater than 1, or L is infinity, which is also greater than 1, so I've never understood that, the series diverges. If L is equal to 1, the test is inconclusive, and that's going to be annoying because at the end points of the interval that you get, the test is always inconclusive, so you have to use some other test. This is the main thing that we use to find the radius of convergence. We are going to have to test the endpoints separately. Most of those end up being maybe a p-series or a geometric series. You can use the ratio test on basically anything, but you should never use it on a p-series. 1, because you're wasting your time, and 2, because it 100% of the time is inconclusive for p-series. You especially want to use this if there's a factorial inside of your series and it's not one of the famous ones that you have memorized, like it's not sine, cosine, or e to the x. That's definitely going to be a ratio test situation. I'm just going to put these 3 examples here of how to simplify things with factorials. So we're given an a sub n. We're going to calculate a sub n plus 1 over a sub n. This is the setup for the limit that we have to take when we're using the ratio test. So you can take a look at these. I'm guessing that you've done a lot of these in class at this point, but this is the work that I would show. And then we would have to take the limit to infinity for each of these things. So maybe take a screenshot of this if you want to look. An important idea that we want to talk about that may come up on multiple choice and could come up on free response is the concept of absolute versus conditional convergence. So the ratio test always has an absolute value around the ratio. It always gives you absolute convergence. Here's what that really means. If the sum of the absolute value of a sub n, so if there was a -1 to the n or something weird going on, you just take the absolute value of the nth term. If the series you get from that converges, then we say that the original series converges absolutely. On the other hand, if we take the absolute value of the terms and we get a new series and that series diverges, but the original series converges, then what we would say is that the series, the original series, is conditionally convergent. Then there's the scenario where both series, the absolute value diverges, the original diverges, then overall we would just say that the series diverges. If they don't ask about conditional convergence, you can basically forget that it exists. You do not need to worry about it. Taylor series, power series can only be conditionally convergent at the endpoints of the intervals of convergence. That is often on multiple choice how you distinguish things. Also, maybe they'll tell you the center and they'll tell you that the series is conditionally convergent at a particular x value. They're essentially telling you the radius of convergence at that point because you can only be conditionally convergent at an endpoint. I've done a couple examples here of looking at absolute versus conditional convergence. First one is famously the alternating harmonic series. If we take the absolute value, we just get 1 over n, which we know is harmonic and diverges. We then apply the alternating series test. The terms alternate and decrease in magnitude to 0. So this thing converges by the alternating series test, but diverges when we take the absolute value. That's conditionally convergent. If you look at the next one, we try to test it for absolute convergence. So we take the absolute value of the terms and we basically end up with a quadratic over a 5th degree. We can reduce that down to just 1 over 4n cubed. That's a p-series that converges. So the sum of the absolute value of the terms converges. That means we're done. This is absolutely convergent. We can look at something like -1 to the n cubed over 3n plus 2. When we try to check it for absolute convergence, we get the limit is not 0, so that diverges. But that doesn't mean we're done. We have to then do the alternating series test. We look at this, the limit of that just does not exist, which is not 0, so that diverges. So overall, this thing diverges. Now let's talk about the thing that people mostly think about when they think of Unit 10, and that's Taylor polynomials or Taylor series. So if we have a Taylor series centered at a, that's going to be f of a plus f prime of a x minus a plus f double prime of a over 2 factorial x minus a to the second. And then our nth term is just the nth derivative over n factorial x minus a to the n. Taylor series versus polynomials, you're just going to have a plus dot 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 at the end of your Taylor series. I recommend that when you're writing a Taylor series, you actually include the 0 coefficient terms so that the pattern doesn't kind of get messed up. I find that that happens to me if I skip one of them. So I'll find myself writing 0 over 3 factorial x minus a to the third. When we're trying to determine the interval or radius of convergence for these sorts of things, we're always going to use the ratio test on the AP exam. The radius of convergence is a number, and the interval of convergence is actually going to include testing the endpoints to see on what interval this converges. So when you're looking for just the radius, radius, when you get it down to the absolute value of x minus a is less than something, that something is the radius. Since the ratio test tells you just nothing about the convergence at the endpoints, you're then going to have to test the endpoints using the other tests that we know. Mostly they end up p-series, alternating series, or geometric series. And one weird thing to keep in mind, it's not really weird, it's just a fact. One thing to keep in mind is that the tangent line to a function is the first degree Taylor polynomial. So sometimes in a problem, they'll give you the tangent line and a way to generate further derivatives. You have to recognize that the tangent line is already the first degree polynomial and go from there. And as I mentioned previously, a series can only be conditionally convergent at an endpoint. So when they tell you about that, they're kind of telling you the radius of convergence. Let's take a look at finding the radius of convergence. So if we want to find the radius of convergence for the sum of the quantity x minus 1 to the n over n times 2 to the n, step one is we just look and we see that a sub n is x minus 1 to the n over n times 2 to the n. We set up the absolute value of a sub n plus 1 over a sub n. We simplify that down as much as we can. So we get n times the quantity x minus 1 over 2 times the quantity n plus 1. Now we have to take the limit to infinity. So the x always stays an absolute value. If there's a center, it'll always end up ultimately the absolute value of like x minus a. So we have the absolute value of x minus 1 over 2. That's our limit. So we automatically know that this thing converges automatically for L less than 1. So the absolute value of x minus 1 over 2 is less than 1, which means the absolute value of x minus 1 is less than 2. As soon as you isolate the absolute value of x minus the center, the thing on the other side is the radius. So here the radius is just 2. Also, I should emphasize, pay attention to what they're asking for. You do not want to waste time finding an interval of convergence if all they were interested in is the radius. And conversely, if they want the interval, don't stop when you get the radius. You also have to check your endpoints. And we should probably take a look at an interval of convergence problem as well. So we have here, find the interval of convergence of the sum of quantity x minus 2 to the n over n times 3 to the n, a pretty similar problem. Again, we calculate our ratio, the absolute value, then we take the limit. We end up ultimately with the absolute value of x minus 2 over 3 is less than 1, which tells us the absolute value of x minus 2 is less than 3. So you're at 2 and you can go 3 in either direction. So you converge absolutely between -1 and 5. Now you need to test the endpoints because the ratio test was inconclusive at each endpoint. You take -1, you sub it in, you get -3 to the n over 3 to the n, which is just -1 to the n. So we have -1 to the n over n. That definitely converges by the alternating series test. Then we take the other endpoint, 5, we sub it in, we get 5 minus 2 is 3, so 3 to the n over 3 to the n, that's 1. So we get 1 over n, which is the harmonic series and diverges. So the last thing we want to do is just write down our interval of convergence. We converge at -1, so it's included, and we diverge at 5, so it is excluded. Now we're going to run through a couple of classic Taylor series problems. So one of them is to find the nth derivative at a given a Taylor polynomial. So if we have the 4th degree Taylor polynomial is that thing written there, and we want to find f prime of 1, f double prime, f triple prime, and then the 4th derivative at 1. So we know that the nth derivative over n factorial is the coefficient of x minus a to the n. We just take advantage of that. So if we're looking for f prime, we find the x minus 1 to the first term. Its coefficient is 3. So f prime of 1 over 1 factorial is 3. F prime of 1 is 3. We can keep doing this. F double prime of 1 over 2 factorial has to be equal to -2/5 because that's the coefficient of x minus 1 to the second. So from that we get f double prime is equal to -5. Notice that there is no x minus 1 to the third term. That means that the coefficient must have been 0. This is kind of one of the keys to working with this. So the third derivative over 3 factorial is 0. We automatically know that the third derivative was 0. And then we can do the 4th derivative in the same way. So just to reiterate, if there's a missing term, it means that the coefficient of that term was 0. So the nth derivative over n factorial is equal to 0 for that particular value of n. Another sort of classic problem that we have to do is sometimes build the Taylor polynomial given a formula for the nth derivative. So if we are given that f of 2 is 1, f prime of 2 is -1, and then a means of finding the nth derivative at 2. So it's -1 to the n, quantity n minus 2 factorial over 3 to the n for n greater than or equal to 2. What we want to do is find the 3rd degree Taylor series for this thing. What I recommend that you do is make a table of values where you're going to have n and then you're going to have the nth derivative at 2. You can immediately fill in that the 0th derivative, the value of the function is 1. The first derivative is -1. And then for 2 and for 3, because we're going to the third degree, what you do is just replace every n that you see in that formula with a 2 and then with a 3. So we end up with -1 to the second. 0 factorial is 1 over 3 squared, so 1/9. And then we get -1 cubed, 1 factorial, which is 1 over 3 cubed, which is -1 over 27. And then we just plug into the formula we memorized, right? So it's the nth derivative over n factorial, x minus a to the n, which is consistent for the first term. It's just that you're plugging in 0 for every n that you see. Sub them all in, we get our polynomial. There's no need to simplify it more than that, so we will leave it. Definitely make a table on these sorts of problems. It makes it easier ultimately to check your work, which is really important. All right, another incredibly common thing to do on free response in particular is to find a series for the integral from a to x of f of t dt. So if we are given a Taylor polynomial or a Taylor series for f of x centered at x equals 3, as you can see above, we want to find the first 4 non-zero terms and the general term of the integral from 3 to x of f of t dt. One thing to notice is that the original is centered at 3, and then for this one we are doing the integral from 3 to x. So what's going to end up happening is when we plug in the 3 for the lower bound after doing the integral, every term just kind of like disappears. This is a definite integral, and we are not going to have to solve for c, I guess is kind of the point there. You just set this up, change every x that you see up above into a t. You can write the integral from 3 to x f of t dt is the integral from 3 to x of 2 minus 3 quantity t minus 3 plus 4 quantity t minus 3 squared. They always ask you, well, they pretty much ask you for one more term than the terms that you had previously. So you always have to like use the pattern to find something. So this is just reversing the power rule. So you do +1 times the reciprocal. That 2 becomes a 2t, and then we plug in x and 3, so we get 2 quantity x minus 3. Then that minus 3 quantity t minus 3 becomes -3/2 quantity t minus 3 squared. And when we plug in x, we get -3/2 quantity x minus 3 squared. When we plug in 3, we just get 0, so that term is gone. Same thing will happen to the next thing. We have 4 quantity t minus 3 squared. You reverse the power rule, so you add 1 times the reciprocal. 4/3 quantity t minus 3 cubed. Plug in x, and you just get it with an x plugged in. Plug in 3, and it goes away. To find the next term, what I'm going to do is just look at the pattern, right? So we're alternating the signs, so it's going to be negative. The numerators, we're just counting up, so it's going to be 5. The denominators, we're also just counting up, so it'll be 4, and then an x minus 3 to the 4th. For the nth term, I'm just going to add 1 to the exponent to get n plus 1, multiply by the reciprocal of that, so that's 1 over n plus 1, and keep the original coefficient. And that's how we can get the series. They ask this all the time on the FRQs. It's very straightforward, but a lot of people unfortunately skip it, so do not do that. You can definitely get these points. You're sometimes going to be asked to find a series that has a new center. So say we're given this series, which is definitely centered at x equals 2. We want to find the first 3 non-zero terms and the nth term for the series for g of x, which is f of x plus 2. And then the question says our series will be centered at 0. Do not worry about that. Every time they ask you to do that on the AP exam, you're just going to end up getting exactly the center that they asked for by doing a composition. So g of x is f of x plus 2. You look at f of x, every x becomes an x plus 2. So if you want to use the summation, it's the x in x minus 2 becomes an x plus 2. So now you have x plus 2 minus 2, which is just x to the n over 3 to the n. And now you can just write out your terms. I'm not kidding. They ask you to do this somewhat frequently, so don't be freaked out about it. It just works the way it should work, and you move on and get those points. Another really common question that you're going to be asked is to find a series for f prime. So that may be given in summation to begin with, or it may be given term by term. My recommendation is to just work on it term by term no matter what. So if we have the sum from 1 to infinity of -1 to the n plus 1 times x to the n over n, we want to find f prime. So the first thing I'm going to do is I'm just going to write out a bunch of terms of f of x. That's going to be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc. And then literally take the derivative of each term. This is how you take the derivative of a series, is you write out the terms and you take the derivative. So the derivatives of all those ultimately give me 1 minus x plus x squared minus x cubed plus x to the 4th. I can find either by taking the derivative of the nth term or just by generalizing the pattern that the nth term of this thing, of the derivative at least, is -1 to the n plus 1 and then x to the n minus 1. And then from there, if I need to write it in summation form, which on the exam you basically never need to do. I could write it in summation form, or I could find the sum, which you are way more likely to be asked to do. So by dividing consecutive terms, I can see that negative x divided by 1 is negative x squared divided by negative x is also negative x. So the ratio is negative x. I get my first term 1 over 1 minus the ratio, so 1 over 1 plus x. And just kind of a reminder, I've noticed that on FRQs, they frequently just ask you for more terms than what you initially are working with, so you do have to use the pattern to generate another term. Be on the lookout for that. Another exceptionally common type of problem is to find a Taylor series from a table that gives you a bunch of derivatives. So here's our table. We want to find the third degree Taylor polynomial. This actually, at this point, probably feels really easy. You just write down the formula. So you just write down the formula. That's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial times x cubed. Then we can just substitute the values in. You could simplify or not simplify. It doesn't matter on the free response. Multiple choice, obviously you have to choose whatever they give you. This is a very straightforward type of question, and I hope that this shows up on the exam for you. All right, it's time. Let's talk about Lagrange error bound. So the Lagrange error bound puts a bound on how wrong you can be when you use a Taylor polynomial. So if you have a degree n Taylor polynomial centered at x equals a, the most you can possibly be wrong, the error, is less than or equal to m than the absolute value of x minus a to the n plus 1 over n plus 1 factorial, where m is less than or equal to the maximum of the absolute value of the n plus first derivative on the interval from the center to whatever you are plugging into the polynomial. So m is definitely the most mysterious part of this. I always look at the error term and I think it's basically like the first term left off, just like when you're using alternating series error, except instead of actually being the magnitude of the first term left off, we have some upper bound. Instead of just using the n plus first derivative, we have to use the maximum of the absolute value of the n plus first derivative on the interval. But it's really similar to the first term left off. They will always communicate m to you in some way, shape, or form. So they may give you a graph and you have to recognize that you need to take the absolute value of that graph and then find the maximum on the interval. They may just outright tell you the absolute value is always less than or equal to some value. They're going to find a way to tell you because they don't want to have to deal with 150,000 people coming up with their own value of m. They'd prefer to have a very clear choice for you to make. Let's take a look at a kind of classic Lagrange error example. So we are given the third degree Taylor polynomial. It is used to approximate f of 5.9. We know that the fourth derivative is positive and increasing for all values of x. And we know that the fourth derivative is less than or equal to 5 for all values of x. So what we want to do is find an upper bound for the absolute value of f of 5.9 minus t sub 3 of 5.9, which is a weird way of writing the error, and that's how they often write the error, so you should definitely be on the lookout for that. Here's my solution. Since I know that the fourth derivative is increasing and less than or equal to 5, I'm just going to use 5 for m. I'm going to set up my error and say that it's less than or equal to m, the absolute value of plug in the value, so 5.9 minus 6, to the fourth, because we use a third degree polynomial, we're using the fourth derivative here, over 4 factorial. That's less than or equal to 5, our value for m. The difference between 5.9 and 6 is negative 0.1, but we're raising to the fourth, so it doesn't matter. Also, there's absolute value, so it doesn't matter. Over 24, that works out to 1 over 480,000, which is definitely way less than the 3 decimals they require on the AP exam. But I do think, I haven't really checked this, I think if they give you an exact value, they just don't really care about that. But we can then just say that our error is less than or equal to 1 over 480,000. That's our error bound. Now I want to kind of look at this visually, so a little animation. We're going to find another Lagrange error bound problem. Function that we're dealing with this time is going to be approximated by Taylor polynomials that are centered at 0. So those are also called Maclaurin polynomials. And so we have 2 minus x, and then we have 2 minus x plus 1/3 x squared, and then we have 2 minus x plus 1/3 x squared plus 5/12 x cubed. Okay, so those are our Taylor polynomials, and what we want to do is approximate error in using them. What we're doing is we're going to find a bound for the error in using these polynomials to approximate the value of the function. The error bound is less than or equal to m over n plus 1 factorial, absolute value of x minus a to the n plus 1, where m is the maximum of the absolute value of the n plus first derivative on the interval from what you're plugging in to the center. So in this case, the center is 0, and we're going to be plugging in 0.5. All right, so the first step, we're going to use the tangent line, which is the first degree Taylor polynomial, and we're going to sub into the polynomial 0.5. We are trying to find an upper bound on the error, which is the absolute value of the true value of the function minus our approximation. So we can write it out, right? It's just going to be the error is less than or equal to m over 2 factorial, the absolute value of 0.5 minus 0 squared. That we can simplify down right away to m over 8. The real question becomes, what's m? Well, in this case, m is less than or equal to the maximum on the interval from 0 to 0.5 of the absolute value of the second derivative. So let's see what that looks like. And here's a graph of the second derivative. To find m, we need actually the absolute value of that, so we can just transform it. Everywhere that that graph is negative becomes positive. We are only searching on the interval from 0 to 0.5. So on that interval, if we zoom in, we can see there's a little maximum there, and it's approximately 1.042. And so m is less than or equal to that value, that 1.042. So if we go back and we look at our formula again, we're going to substitute that value in and see what it simplifies to, right? So we plug that in and we simplify. This would be calculator. So we get that our error is less than about 1.303. And I think it'd be good to look at another one. So if n is equal to 2, we're using the second degree polynomial, which means to find our error, we're going to take a look at the absolute value of the third derivative, because we are using the second derivative to make our polynomial. So we need to find this value of m. And here's a graph of the third derivative, which you can kind of see is just linear in this case. Then when we take the absolute value, that should be sharp turn, but you know, good enough. We can find the maximum anyway. We zoom in, we get this. We're looking for the maximum value. It occurs at that left endpoint, so 2.5. So m is less than or equal to 5/2 or 2.5. And we can go back to our formula. And once we're back there, we're just going to substitute in again, and we get a bound for our error. So in this case, 0.0521. Now, one thing I just want to point out is that in doing this process, when you go from using only n equals 1 to n equals 2, the more terms you use, the more accurate your answer should be. So the smaller your error should end up. And a lot of that will have to do with the interaction of like the n factorial, and you're raising things to a higher power. But the higher degree you use, the more accurate you are. There's a couple series that you must have memorized by heart. Those are e to the x, which just has n factorial in the denominator and you get every single term. Sine of x, which only has odd powers of x and alternates. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So you end up with a general term of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. You have cosine, which only has even powers of x, including x to the 0, which is 1. So we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. The nth term is -1 to the n, x to the 2n over the quantity 2n factorial. So that's an even factorial. Sine has an odd factorial. E to the x just has n factorial. That's how you can tell the difference between the famous series is you look at the denominator, what factorial are you dealing with? And then 1 over 1 minus x is actually just the geometric series, but it turns out a Taylor polynomial. So that's going to be the sum of x to the n. So 1 plus x squared. It does not have a factorial. It looks geometric. And that's the only one that doesn't converge for all x. That has to have the absolute value of x less than 1 because it's geometric. You need to memorize these because literally sometimes they give you a point just for writing down a couple of the terms. So you want to be able to get those for sure. Also, we're just going to work with them in a lot of ways. One thing you're certainly going to do with the series that you have memorized is compositions, which means you're going to take a monomial, like a times x to the n situation, and just sub it in for every x that you see in the original series. So here on this slide, I have sine of 3x squared, I have cosine of x over 2, and I have e to the 4x. Definitely take a look at those. I'm just going to let you screenshot that and think about it. I'm going to move on to the next topic. Okay, the last thing that I want to talk about, literally the last thing in AP Calculus at this point, is how you can find the product of a bunch of series. So you can actually just multiply Taylor series. So for example, here, what I want to do is find the 5th degree Taylor polynomial for e to the x times sine of x. What I'm going to do is I'm going to write out both of the series up to and including the 5th degree. If it was an even thing, I would only go up to the 4th, because obviously if you're already at the 6th degree, you're not going to get a 5th degree thing out of it. So e to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, x to the 5th over 5 factorial. Stop there. Sine of x, we need x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. But that's all we need. Now what we're going to do is multiply them. So I've kind of color-coded them. So to multiply these, we literally just do polynomial multiplication. But we have to be careful because we only want to go up to the 5th degree. So I'm going to take the entire first thing and I'm going to multiply by x, because if I multiply every term in the first thing by x, the highest degree I end up with is x to the 5th. Then I'm going to take the entire first thing, except not the entire first thing, and multiply by negative x cubed over 3 factorial. X cubed times x squared is x to the 5th, so I'm going to disregard the x cubed and the x to the 4th term, so I'm just doing negative x cubed over 3 factorial times 1 plus x squared over 2. Then I'm going to take the x to the 5th over 5 factorial, and the only thing I can multiply that by is 1 and stay at or under the 5th degree, so that's what we do. Then we kind of simplify this. Never clear to me on the AP exam if we need to really clean this up or not. I mean, collecting like terms and polynomials, I don't know. Anyway, I did simplify it and I ended up with x plus x squared plus x cubed over 3 plus no x to the 4th and then minus x to the 5th over 30. I don't really think you would need to simplify that. I think at most maybe you would like group all the x terms, the x squareds, the x cubes, the x to the 4th, the x to the 5th, maybe. I don't know if that's a low note to end on, but that's been an AP Calculus review. So I hope this was helpful and good luck.